All right, guys. Good to see you again. Let's talk about this. We're going to do topic 7. I don't know if I can pull it off in this session. I may have to combine it in 2 sessions. But I'm going to try to do some problems for topic 7. Problems 13, 17, 39, 44, 51, 53, 71, 75. I mentioned that in the other video where I ended up just staying with topic number 6 because the rocket problem proved challenging and fascinating enough that we had to stay with it for a long time, at least in my opinion. But this is what we're going to try to do. We're doing this. So, with this in mind, we're trying to do this. Let me talk about a few things related to it. Topic number 8 is really similar to this. So I'll see when I do get to topic number 8 what I'm talking about. Basically, for topic number 7, we're talking about rotational motion and gravitation. Let me give you some of the highlights of this thing and kind of figure out where we're going to go. You guys remember, we've said a lot of stuff. I mean, we did say that distance travel, and that was going to be a little loose in the interpretation of some of this stuff. I think if I get too technical with it, it's going to take way too long. And I think sometimes we might miss some of the broader connections that are present, in my opinion. It's your call. In the end, remember, when you're talking about velocity and when you're talking about acceleration, those are vector quantities. Regardless of how loose we are in terminology, if we're trying to speak in a colloquial sense, just so we get the point across, we never forget that velocity is always a vector quantity, acceleration is always a vector quantity. The magnitude of acceleration and magnitude of velocity are frequently what we say. We just don't deliver that speech in that manner. But again, velocity and acceleration are always vector quantities. Well, you guys remember at this point, back in the day, and we're talking about constant acceleration. We're talking about constant acceleration. We've got Vf plus Vi over 2 times t. Say, what are you doing, Bailey? You know this already. Well, you're about to see what I'm doing in a second. You're about to see all this stuff in a second. So, okay, we said this, we worked around this a little bit. And we said, no, real broad statements here. We said A is Vf minus Vi over T. From there, a lot goes on. We can play a lot of games here, you can say. You can say this right here is Vf. Look, bottom line is in the game we play, we're just playing games with mathematics. Mathematics is valid. If it's valid, it's valid, and that's the story. You go something like this right here. We can say this. Remember, with the rocket problem, we were basically doing a rip-off of this. But with the rocket problem that I was trying to do, wow, that A was not constant. That A was variable. The A with or without gravity is variable in the sense that we talked about earlier in that rocket problem from topic 6. And we have a camera. In this case, we'll say it's constant. In this particular case, for these circumstances, it's constant. So we got something looking like this. Going on, we played a lot of games with this stuff already, you guys. You don't need to deliver these speeches all over again. Sounds good to me. Well, okay, kind of talk. And will make some sense. I'm glad in a lot of ways that we broke this up, that Serway and Vuille broke this up into 2 chapters. Topics 7 and topics 8. So let's kind of take it as well as we can. I gotta talk to you. There are a lot of ways you can write an angular measurement for theta. You can use revolutions, you can use degrees, you can use radians, you can probably make up your own units very easily as long as you're mathematically consistent and you can convert things back and forth, which you can, consistent mathematically. It all works. The one that works the best is this special unit measure known as the radian. The radian is probably the most natural of all the degree measurements. In fact, it is the most natural of all the degree measurements. Why is that? Because the radian is a ratio of arc length to radius. The scale of the radian, the way radians behave, they are scaled scaled the same way as the number system that we're used to seeing is scaled. We talk about the complex numbers, we talk about the imaginary numbers, the real numbers, the complex numbers, and they all have a scaling of the measuring stick from 0 to 1. On the number line, that measuring stick from 0 to 1 helps us build the negative numbers, the imaginary numbers, the complex numbers. That measuring stick from 0 to 1 helps us build fractions, everything. That's the measuring stick of everything in mathematics that I understand. I don't know what other people know, so I'm just going to tell you what I know. Everything that we're encountering, that measuring stick from 0 to 1 is really, really immensely huge. It is a measuring stick of everything that we're going to be looking at, period. If that is the case, the radian is scaled to that measuring stick from 0 to 1. The degree is not. The revolution is not. Though we can even argue that way. There's ways you can argue and say, yeah, no, you're wrong. They are. The most natural, we can argue that a bunch of ways, but at least in and of itself, the radian tells you a lot. What is the radian? If you're here, and this is a radius of an arc, and this is the length of the arc that is traversed, and that is a distance s. And this we call theta in radians. Theta in radians is the length of the arc divided by the radius. Wait a minute, this is feet and this is feet. Or this is miles and this is miles. Or this is kilometers and this is kilometers. Or if this is light years and light years, so you want to go that way. Or if this is meters divided by meters, it's a unitless quantity. This thing is scaled most naturally according to the way the number line, according to the way the real number line is scaled. This is scaled identical to it in a sense. This can actually tell me that there's a fraction of a radian, there's this, that, the other. Again, there's a lot of ways to argue this. I don't want to get into that big argument now. I wish I had you guys in front of me, we could get into it a little bit more. But for our purposes, this is big, and this is the radian, this is the radian. Okay? This is what they like to use. And the very beautiful classic theorems in calculus that talk about trigonometry, the trigonometric functions, Taylor's theorem. So often, if not exclusively, I don't want to get too much into this, we've got that. E to the I theta equals cosine theta plus I sine theta. This is used with radian. When you want a Taylor series expansion for the cosine theta or for the sine theta by themselves, these trigonometric, this Taylor series expansion of these trigonometric functions uses the radian. If you use any other angle, you can still make it work, but you've got to convert those angles to radians in some form or another. The radians are of huge importance. But again, you can use all the other ones. Just make sure you're doing things right on your calculator. Your calculator's according to radians, if you're using radians, or your calculator is according to degrees, and so on and so forth. One complete revolution, that's a degree measure. It's one complete walk around. From here, walk all the way around to here, or from here, walk all the way around back to here. That's one revolution. That's 360 degrees. That's 2 pi radians. Really? Yeah. If you go all the way around, how long is that? Well, isn't 2 pi r the circumference of the circle? That's a big arc. It sure is. It's a big arc called the circumference of the circle. Divided by the radius, that's the arc length divided by r. In this case, it's 2 pi. There are 2 pi radians to go all the way around. There are 360 degrees to go all the way around. There's one revolution to go all the way around, and people tinker with that. They look at this thing right here, you can do a conversion factor on that. You can make it 360 degrees divided by 2 pi radians. And that comes out to 180 degrees divided by pi radians is a conversion factor. If you flip it upside down, you get another conversion factor. What are we talking about? If I want to go from radians to degrees, I use this conversion factor. When I want to go from radians to degrees, the radians are on the bottom. When I want to go from degrees to radians, I use this conversion factor. Get it done. So, it's looking pretty good that way. What else do we know? Well, let's come back over here. If you wanted to find out the limit of the arc, and you knew what theta was, and you knew what r was, but you did not know the arc limit, why don't you multiply by r inside and see what happens? The length of the arc is theta divided by r. The length of the arc, s, you can also call it d if you want, for distance. Distance equals theta times r. Wait a minute, you just hit box something pretty big. Distance and angular measure, if it's in radians. If it's not in radians, ladies and gentlemen, you've got to play some mathematical games to get it in radians. That's how important it is. R times theta or theta times r. So are you telling me for me to go from theta to a distance, I'm multiplying by r? Well, there's a lot that tells you. There's a lot this means. I wish, there's a part of me wants to do this real rigorously and old school, but there's only so much time people have, so we gotta figure out how we're going to say this. Okay? But we have what we have. We got what we have here. Let's talk. All right. You see what I'm saying here? You've got it. Okay, let's see what we have here. So, I wrote the whole song and dance early on in the discussion, right here, you guys. I wrote the song and dance right here. What do you say? I tell you something. In the angular realm, there is a correspondence. D looks a lot like theta. B looks a lot like the Greek letter omega. The Greek letter omega, that's the lowercase letter omega. That's the last letter of the Greek alphabet. Alpha is the first letter of the Greek alphabet, omega is the last letter of the Greek alphabet. So that's omega, that W kind of looks like W. It's actually a lowercase omega. A, regular acceleration, corresponds to the thing called angular acceleration. Let's see here. For right now, that's about all I need. There's the correspondence. Tell you what I'm going to do. You tell me how you feel about it. Didn't I just deliver this speech? D equals theta times r. Great. Can I ask you another question? Would V be equal to D divided by T? Fine. If theta times r is D, divide that by T, you got this. I'm going to talk to you. Theta divided by T is this thing called omega. Omega r. What just happened here, guys? That's theta divided by T, that's omega. Omega is theta divided by T. Wow, that looks a lot like D being equal to D divided by T. If you put, in place of D, if you put theta, in place of D, if you put omega, wow, there's a correspondence. Let's see, is there a real correspondence over here? D is theta times r. T is T. D divided by T is D. Theta r is D. D divided by T is the B. Yeah, I know, but when I say that theta divided by T is omega, omega r, wait a minute, there's a connection here. Yeah, at the end of the day here, you guys, you got D is theta times r. V is equal to omega over T times r, theta over T times r, which is omega r. And the acceleration is an interesting matter in its own right. Didn't we say acceleration with VF over VI divided by T? Didn't we say that V is omega times R? I'll say omega F times R. VI is omega I times R divided by T. Wait a minute, we gotta talk. Pull a knot out there. Pull a knot out there, guys. Wait a minute. Didn't we say that A was VF minus VI over T? Well, alpha is the analogy. Instead of VF, it's omega F. Instead of VI, it's omega over T. This right here is the angular acceleration. It's not the most rigorous look at it, guys, but man, look at it. There's a lot going on. One thing going on here, another going on there. That's A. This is alpha. Now I'm a Greek guy, I don't even know how to make the Greek alphabet. What's going on? A equals alpha times R. Wait a minute, there's something going on here. Theta looks like D. Omega looks like B. Alpha looks like A. And in fact, when you multiply each of the entities by R, you're getting B equals theta R, B equals omega R, A equals alpha. That's huge. What's really going on here? Well, there's a lot going on here. I guess if I want to make a move, guys, there's a lot going on. If I want to make a move from the angular realm to the linear realm, I take the angular realm and multiply by R, and I get here. Angular velocity times R gives me linear velocity. Angular times R gives me distance. Angular velocity times R gives me linear velocity. Angular acceleration times R gives me the acceleration. So angular times R gives me the linear distance. It's a curved distance, really, but it gives me the length of the curve, the length of the arc. Theta times R gives me the length of the arc. If you're using radians, there's only worth for radians. You gotta be radians. Theta times R gives you D. The angle times R gives you the distance. The angular velocity times R gives you the linear velocity along the curve. It is taking a curve. The angular acceleration times R gives you the linear acceleration. Crazy. Well, it's kind of similar to that. We talked about the analogy. I think we reported on analogy. I'm going to leave it up there. We'll talk more. When we get to complicated, we'll talk more about this. But, so let's see what we have. What's going on? Well, I think, we already filled these birds with one or two stones already. Let's just kind of like document it a little bit if you want to go there. Theta is the average omega times V. I'm going to write a couple things down. I'm going to start walking around and doing something to think about. Theta is the constant acceleration line. We have this right here. Then there's a couple moves you got to make here, as you can say. I mean, alpha equals omega F minus omega I over T. T equals omega F minus omega I over alpha. If you ever have an option to be left-handed or not, choose not to be left-handed. I don't know, maybe not. I don't know. Let's see. The left-handed is actually good for me. It can be good. I don't know. There's a lot of random stuff that goes on. It makes it hard. But, so let's see what we got here. I've always had right issues. So anyway, here we go. So it's not one of those beautiful lines. I didn't see it, guys. Won't come from here. So alpha's I'm going to appeal to your common sense on this stuff as best I can. Let's see what we got here. All right, a little lot of stuff down here. If this stuff looks familiar, I hope it does. It should look familiar. A long time ago, ad nauseum, I wrote all this down, and I wrote all that down. I got some words for you. Over here, wherever you see a D, put a theta. Wherever you see a B, put an omega. Wherever you see an A, put an alpha. When you do so, these quantities right here that I have, these quantities right here are mathematically, these quantities right here are mathematically identical to these quantities right here. Period. It's a huge significance. It's going to help us for working around trying to get this thing under control. There's different kinds of accelerations that can take place. The book itself doesn't go there. There's, I think, as a mutual acceleration, I'm not saying it the wrong way. There's Coriolis acceleration, there's centripetal acceleration, and there's acceleration, the linear acceleration. They're going to talk about centripetal acceleration and regular acceleration. Well, okay, guys, I got to judge how I want to do this and at what level we're taking this thing. But here's what we're doing. If something is spinning around like this, and you got this thing, here's the object, and it's spinning around with a linear velocity of v, and the radius here is r. And there's some neat proofs on this. I think the book goes into it. I'm unfortunately not. I just wish I had more time, guys. I wish I had more time. None of us, other people doing this right now are going to have a lot of time. Other people are going to be doing the same work I'm doing. They're going to have to pick and choose how they go about this. And hopefully, like I said, hopefully we get to see you guys soon. If not, we'll put as much down as we can. I'm also using stuff from a previous semester where I've done some of the later stuff with this crisis that happened. So we should be in decent shape. I'll always figure it out as much as we need to. This thing's spinning around with velocity v. Let's pretend this thing that you're doing a bird's eye view. You're above this thing, and this thing is on a frictionless table. This thing's on a frictionless, it's a frictionless environment, it's a frictionless table, and it's spinning around. And there's no gravity. Gravity's not playing a role in this. If it did, we have to talk about it. And we may have to in the future. But right now, I've got a bird's eye view of this thing, it's spinning around like this. What is the acceleration? The acceleration, look, anybody who's ever spun something around over their head, or if you're an Olympic athlete and you're throwing the hammer, you call it the hammer throw. They spin around that cage and they throw something out. Those people have to hold on to that thing really hard. The faster they spin and the tighter the circle they bring that thing that is as massive as a shot. I think it's the same size as a shot. It's as massive as a shot. The more mass of the object and the faster they spin it for a given radius, the more force they got to put on it. I'm going to try to make a long story short of this, because you've got a feeling. The centripetal acceleration is an acceleration, the true centripetal acceleration is an acceleration that goes inward. How do you know that's true? Because I better be pretty strong. If I'm spinning that hammer around, I have to be able to hold it. It ain't, that hammer wants to leave the circle, if you want me to say that. You have to hold that thing in the circle. And there's a neat proof of this, the book chapter coverage of it as well. Right now, I'll tell you exactly what's happening. The faster you spin this thing, and the tighter the circle you make, real fast speed, real small radius, means great acceleration that you've got to provide. Even, you see what he's talking about. This thing's going at velocity v. Or at least magnitude velocity v. You're not changing the velocity, guys. What are you talking about? I thought acceleration happens when you change velocity. Well, yeah, you are changing the velocity. You're changing the direction. This thing constantly wants to leave the you are yanking it into the circle. You are forcing this guy, to stay. This guy wants to fly out this way, he wants to fly out that way. You're not allowing that to happen. You are constantly bringing this guy into a circle. And there's some stuff you can do. I don't have the time to show it, unfortunately. There's a neat intuitive proof as to what's going on for the conclusion I'm about to show you right now. But for our purposes, what we know is this. That if you've got this thing going around real fast, and you keep it in a circle, the faster it's moving, the more force you've got to put on this thing to keep it there. Really? Yeah, really. Not only that, you're applying that force. Depending on me, and the tighter the circle, the harder it is. I'll make this as straightforward as I can make it. The centrifugal acceleration is v squared over r. What does that mean? If you got it moving really, really fast, you got a lot of acceleration you're putting on this thing. If r is a small number, the tighter the circle, the more force. You got to put a tight circle on this thing, and you got to go a velocity of v. The best Olympic athletes that throw the hammer in track and field, the hammer throw, they are moving that object very, very fast in a relatively tight circle. They let it go, it's really moving. That is the centripetal P, a P in there. The centripetal acceleration. This is the real acceleration. There's a made-up acceleration they call the centrifugal acceleration. This made-up acceleration is, wow, it feels like this thing is trying to force itself to get out. And it's got the same magnitude as this, and sometimes that's an interesting, and I can say useful mathematical ploy to use in some occasions. Let me see if I can actually get to it one of these days. We may talk about it one of these days, if we have the time. But this is what they mean by this. So what is the force? Centrifugal. Guys, didn't we say that force was equal to mass times acceleration? So that's mass times the centrifugal acceleration. We actually calculated an Olympic athlete at the time through the hammer, his force. You know what it was? They were putting somewhere on the order of 700 to 800 pounds of force. When they were spinning it around to make that thing happen, the world record holder, at the time it was Yuri Sadiq was the name of Soviet Union, at that time Soviet Union. 1988, I think it was something on the order of 350 pounds. 350. Forgive me, like 770 pounds. It's hard to put it out. Some on the order of 800 pounds. 750 to 800 pounds. I can't remember, I don't have it in front of me right now. He's close to 800 pounds. That's strong. He's got to be. He's not going to get the speed that he was doing. What do you mean? Well, the mass is very large. If it's very massive and you're going very fast, then you square it. Divide by a small number, you get a huge answer. Alright, so we talk about that. A lot of times when you get into the level of, you want to talk about, a lot of times you want to talk about, let's say, orbits that take place. There's an orbit in low Earth orbit, something like that. Let's see what we can say regarding that stuff. Well, I'm going to say something. I don't know if you want. Let's call this Earth. Let me say a couple things and kind of come right back to this and see what we can say. Let's talk about Kepler's laws, you guys. And we'll take it from here. Even if I don't do anything and say, yeah, I'll do it tomorrow. We'll get Rick's piece tomorrow. And maybe separately discuss some topic related to the topic on rate and figure out what that is. And I think we'll be okay. We're in good shape. So, let me, right now, if you said what I said here, you got this in the back of your mind, so oh, it's a tap about this stuff for time. Likely going this stuff tomorrow, you guys, and then we don't have to do any election. We can just do a lot of problems pertaining to it. So, got this. Okay, remember what we got here. Maybe I'll just leave it there for now. We talk about Kepler's 3 laws of motion and how they pertain, you know, circular orbits and things of that nature. There's some approximations that we make on this, we're allowed to do so, and we've got some stuff we can say to you. Basically, what I can tell you is, remember I was talking about that Olympic athlete. This is the centrifugal acceleration, and mass times centrifugal acceleration gives you the centrifugal force. What does that mean? Well, that means his arms and body that be as strong as this to make it happen. In addition to that, the rope that is holding that mass, the wire that's holding that mass, better be how strong? Guys, it better be at least this strong. What if there's a satellite going around the Earth? How strong is that going to be? Well, there's no cord holding that up. There's no rope holding that up. The imaginary rope that's holding it is called gravity. And that gravitational pull better be as strong as the centrifugal force that is required to get the job done. Remember that, and get right back to it. Anyway, Kepler's 3 laws of motion. And I do want to say one thing on the side here. As we do this, there's some different things here, like I said. And I have, forgive me, I have all of these problems fully solved for you on campus. So we can't get to it right now. We'll maybe get back to it some point in the future. At least it's on campus already, so you can kind of look at that and figure out what we're going to do. All right. We talk about Kepler's laws. And essentially, Kepler, 1, 2, and 3 on this thing. And let me kind of go with that. That's going to be pretty important for us as well. When we do it. Another thing I want to say is, you know, scalars act like money. Vectors act like triangles, if you allow me to use that language. Scalar quantities act like money. What do I mean? Well, there's a mass of 500 kilograms, and then onto that 500 kilogram vehicle, you add a mass of 1,000 kilograms. That would be the vehicle we're holding. What is the total mass of the system? Well, it's 500 kilograms plus 1,000 kilograms. It's 1,500 kilograms. It adds like money. 500 plus 1,000 is 1,500. Vectors act like triangles. So if you have an acceleration, you have like a velocity here, v sub x, and you have velocity here, v sub y. This guy's v, this is theta, and man, there's every song and dance in the book you can do on this one, right? I mean, you can say essentially, v squared equals vx squared plus vy squared. V equals the square root of vx squared plus vy squared. So on and so forth. Vy over vx, tan of theta. You keep playing games, you get the inverse tangent of theta to get what you got to do. Does this work if you got acceleration? Yeah, it would be an AX acceleration, AY acceleration. Total acceleration is A. This is theta, this is 90 degrees. A squared equals AX squared plus AY squared. A equals the square root of etc., etc. The same mathematics apply. All right, let's talk about Kepler's 3 laws. Kepler's three laws, 1, 2, and 3. First law, second law, third law. First, second, third. All right, well, they kind of summarize it. We'll get into it a little bit as well. First law, all planets move. Let's say there's a sun, a big planet, big sun, whatever. Number one, all planets move in elliptical orbits with the sun at one of the focal points. 2, a line drawn from the sun to any planet sweeps out equal areas with equal time intervals. 3, the square of the elliptical period of any planet is proportional to the cube of the average distance from the planet to the sun. Stuff's kind of easy to come and set. All planets, it's kind of exaggerated. This is the sun. That's the one focus. This is just an imaginary thing right here. It's the 2 foci. A planet moves in an elliptical orbit around the sun. This guy's got one focus. There's a special kind of ellipse, ladies and gentlemen, and we're going to assume all those focus, we assume that's the one we're dealing with. There's a special kind of an ellipse where the 2 foci coincide. 2 foci coincide where the center of the solar system is, where the star is. There's a special kind of ellipse called a circle. Just like a square is a special kind of rectangle, a circle is a special kind of ellipse. And that's the traveling elliptical orbits for our purposes. We make the assumption they travel in, they travel around a circle, travel a circle orbit, close to it. So that's what we got that way. So, okay, this is interesting. Okay. The other thing is this. Let's go back to the ellipse. I just told you we can assume we're dealing with a circle. We're doing a lot of stuff, but okay. So everybody goes to the elliptical orbit. All the planets go around the sun in the elliptical orbit. There's a special kind of ellipse called a circle. Let's say the sun is right here, and the sun is not our sun only. It could be the sun in another galaxy. There could be a solar system in another galaxy, and that sun, according to the theory, things will travel the same sort of, obeying the same kind of physics when they're doing it. Now here's another thing I want to say. If you, in a period of time t, there is this much area swept out. In that same period of time t, that they don't look like they're the same size. This area and that area are the same size. What does that mean? It means a lot of stuff. First of all, it means if the planet is close to the star around which it revolves, if the planet is close to the star around which it revolves, if it's close to it, it's going really, really fast. V is really fast. Call that V1. If it's far away, it's going at V2. Well, how do these 3 equal areas? If you figured out that you calculated the area here, and you calculated the area there for the same time period, they are equal areas. A1 equals A2. Yeah, how's that? If there's a real long arm right here, guys, if there's a real long arm right here, then you don't need a base to be that long to have a big area. If the arm is short, you need a large base to have the same area. That means in 10 days, this much arc is covered. In 10 days, let's say, this much arc is covered. in the same 10 days, only that much surface covered with the areas of the. So in equal periods of time, equal areas are covered. The third one, they're saying that the period means to go all the way around. All the way around. To come all the way around, the period squared is directly proportional to equal to some constant times the cube of the average radius. The square of the orbital period of any planet is proportional to the cube of the average distance from the planet to the sun. Say it again. The square of the orbital period of any planet is proportional to the cube of the average distance from the planet to the sun. So A is the average distance. You can use A right there, or you can maybe go for C is a constant, some constant. R is the average radius. Man, I don't want to do another calculus problem, and it really lends itself to it, doesn't it? There is a radius here, which ain't that big, and there's a radius here, which is huge, and somewhere in between is probably the average. You're going to make it so it was a circle. What's the average circle that would work? Is really what you're doing. That's a classic calculus problem. We're not going there, but we have gone there. Very recently, in fact. We have gone there somewhere during problem. The big thing here is the cube of the period is proportional to the cube of the average radius, the average distance away from the sun. You use an A in cube it, you use an R in cube it. Prove that. We're going to prove that last one right now. Real intuitive. So what do we got? So we're looking at, again, the third one, the square of the orbital period, that's T. The square of the orbital period of any planet is proportional to the cube of the average distance from the planet to the sun. R is the average distance. You're pretending that's is what it is. And they talk about it very well in the book, guys. Pages 213 and pages 213 and page 214. Let's us figure out what that is. There is. Let's figure this out. There's a lot of averages going on here, man, so we really got to figure it out. If we can somehow get this guy to be a circle, we've got an average velocity and we've got an average radius, so I think that'll work. Got another question to ask. Let's take a bird's eye view of what's going on. Here's the sun. And here's the planet. The sun is capital M. This might be another galaxy. This might be something as massive as a massive black hole. And this is something revolving around that massive black hole. So M could be a different number than the mass of the sun. We'll call it capital M. And it could be another galaxy, it could be our galaxy, it could be our solar system. It doesn't have to be our solar system. Here's the mass of the planet, small one. From the center to the edge, we'll say it's R for an average distance. It's a bird's eye view of what's going on. I got some questions to ask you. There's an imaginary rope holding that planet and whirling it around. That imaginary rope is powered by something called gravity. Yeah, it's better than showing us the centrifugal force. We already delivered the speech on the centrifugal force way over there to the far right. Let's talk. The force of gravity is a universal law of nature. Everything holds everywhere. There is, how I wrote it, G or small g. That's how you want to write it. You write a small g on there. S to D doesn't matter. Capital G, that's why I didn't want to put it capital G here. Capital G is the universal gravitational constant. Big M is one of the masses. Small m is the other mass. The universal gravitational constant universal gravitational constant times one of the masses times the other mass, G times capital M times small m over the square root of the distance between them. Do you understand that the more massive the two objects are, their product becomes very big? Do you understand that the closer they are to one another, from their center of masses, the center of one to the center of the other, the center of this to the center of this guy, center to center. The closer, if R is a small number, there's more gravitational. The closer I am to that black hole, the more gravitational pull there is on it. The further away I am, the less gravitational pull there is on it. Yeah, these are both massive, and you can do it also. Okay. So that's FG. Can I draw G? You understand this guy ain't getting any closer. There's kind of a dead heat here in this F. This is FG. F sub G is holding that guy there. You know what that's equal to? He's got to be as strong as the force centripetal that's being put on it. I've been doing about 10 more minutes, guys. I can get it right around there, 10, 15 minutes. All right. So we got these right here. Do you guys understand that there is a rope holding this small mass? Yes, there's a rope, sort of. It's an imaginary rope. It's called gravity. Gravity has got to be as strong as the centripetal force. So let's see what is going on vis-a-vis all this stuff. I'll probably pick this thing up a little bit in a second. Let's see what we do. Okay, what is going on here? They're making this claim. They are making this claim. Let's validate it. Let's validate it. So you think it's this. A and R is saying that. A and R is saying that. C's a constant. We'll cross that bridge. I just told you the strength of the rope is as strong as gravity is. And gravity has to be the centripetal force. Let's just make it very clear. Centripetal force is the small mass of the planet. V squared over R is how strong that looks. That's how strong the Olympic athlete had to be throwing the hammer, guys. That's how strong the Olympic athlete had to be throwing the hammer. The only thing, that's how strong the rope's got to be. By the way, the rope is this strong. The heck are we talking about? What we're talking about is that FC has to be as strong as the gravitational. The gravitational pull is the rope. The gravitational pull is the strength of the rope, and that imaginary rope, which is the gravitational pull, generates the centripetal acceleration to do the job. The centripetal acceleration is how tense the rope has to be to get the job done. That's the centripetal force. The centripetal force is how strong the rope has to be. That's as strong as gravity. No more, no less. Everything fits under the category of gravity holding this thing together. If gravity is holding it right there, and now I get further away or any closer, gravity is a constant, F sub G. It's not F times G, it's F sub G, right? That's the strength of the rope, that's the centripetal acceleration. Let's write it down. M is the mass of the planet. V squared is this. R is this. This is capital G. Big M, the black hole, the huge planet, the white dwarf, the red giant, the star called the sun, whatever. M, capital M. This is the satellite, this is the planet, this is the planet. This right here will prove this. Let's go for it. Let's get it done. If that's the case, do you guys agree that V, the speed of this thing going around, you understand it goes around the sun, right? It goes around this sun or this planet or whatever it is. Radius R, right? And ask you a question. The period is capital T. The period is capital T. Do you agree that 2 pi times R is the circumference of the circle divided by the time it takes to go around the sun? That's what V is equal. Great, let's put it here. MV squared. MV squared. What's V squared? It is 2 pi R. 2 pi R with a capital T. Squared over R equals G M over R. Yeah, I guess it's okay. I can't emphasize that M is big, right? That's, these M's are small. Tell you what, true. Why don't you divide by small m on this side? And square this thing out and see what happens. Square this thing, you got 4, that's a constant. Square 2, you get 4. Square pi, you get pi squared, that's a constant. R squared, well, it's not really a constant, but it's there. This is T squared right here. There's an R right here. There's an R down here, guys, so forgive me. Let me not step in the way I want to go. We're going there now. I've got this. Let's make sure we got this right. It's looking okay. We got G big M. We got this. All right, you got what you got. I mean, I don't really see where we want to go here. Make sure we have this right. We got this GMM times R. Reason you guys will see this. In about 5 more minutes, I should be on the round bar. I should be able to find out that's what helped me, right?
We just can't go over.
Okay, gotcha. Forgive me. I love lifting this thing. I really do. I made a careless mistake. That's our square, you guys. That's an R. This is our square. That's our square. This is our square. Carol's mistake. All's well that ends well. Here it is. Right? Our square on the bottom. That's what it was supposed to be. This is right. I just wrote it down wrong. That's up here. Okay, so our square on the bottom. Leave it like that. This is our square right here. And that's our square. Should have been the R squared in the bottom. That's my mistake. My mistake. All right. R squared divided by R. The R was here, right? We did this one. It was 2 pi R. It was the quantity 2 pi R over capital T squared. The quantity 2 pi R over capital T squared. You got all that. Got to here squared. R was the R squared, just our time. All right, guys, do math. We're right here, we're good. R goes to R squared, R times, let's go for it. 4pi squared. T squared here. The R stays here. GM over R squared. Let me divide by R on the side. Let me divide by R on the side. If two things are equal, and there's no zeros in here, they're hard. No one. Two things are equal, they remain equal if two things are equal, their reciprocals are equal, as long as they're both non-zero quantities. The reciprocal of this equals this equals that, all of this equals all of that. The reciprocal of all of this is the reciprocal of all of that. So flip both of them. T squared over 4pi squared equals R cubed over GM. Multiply by 4pi squared on this side. T squared equals 4pi squared over GM. Almost there, guys. Look at it. Isn't that what I said right here? T squared equals some constant times R cubed. T squared equals some constant times R cubed. T squared equals some constant times R cubed. 4 is I'm not trying to get, I'm not trying to twist the y side here. Last time I checked, 4 was a constant. Pi is a constant, so pi squared is a constant. G is the universal gravitational constant. Capital M can vary if you're talking about a black hole in another galaxy or in another solar system. If you're talking about a black hole, somewhere else in the universe, or you're talking about a neutron star or whatever kind of star you have. Depending upon the size of the massive planet that's the center of the system, or depending on the size of the star, our star called the sun, or some other star that might be 10,000 times more massive, or if you're talking about a black hole, or a red dwarf, or a neutron star, or like I said, a black hole very massive, that can vary. But for a given system, ladies and gentlemen, for one particular given system that you're considering, capital M is a constant, G is the universal gravitational constant, 4 is a constant, pi squared is a constant, and that's where we're getting it. So it comes out to this. So when you compare these, you can make a comparison within the system. And we get more into that, as we proceed with the semester, things of that nature, but that's a big thing. When you're giving it this, how much more time do I have? 3 minutes. That's it. Let me leave it at that. It's as strong as it is. This conclusion, this guy is the seed. This guy is the seed where we're getting this. And that's really important. Okay, guys? Thank you. Thank you all for your time. And like I said, we'll get to the nitty-gritty of the problems I just mentioned in topic 7 the next time we're together. Just down the background right now. And we can do this. We get to topic 7, the problems themselves, the next time we're together. Thank you all so much. All right, guys, good to see you again. Let's keep going. The sound quality of some of these videos is not going to be great. That's nobody's fault. Everybody's working really hard to get this thing done. It's just that there's a high ceiling and a very big place. It's not going to be easy. So I'll try to speak every bit as clearly as I can. Obviously, all of these notes are in Canvas. So if you're not following me too well, just read my Canvas notes. Those those are very much loud and clear. Also, what I'm doing here, I'll try to write as many things down as possible, so if you don't catch what I'm saying when we do these, wherever I'm going to be located, the next few sessions of taping, wherever I'm going to be located, if you're not hearing me too good or if it's a little muffled, whatever it is, because of the audio quality, just watch how I'm doing it as well again. Okay? Nobody's fault, it's just the reality. Things are what they are. Nobody's fault at all. So, here we go. Topic number 7, number 13, based on stuff I have discussed already, so to speak. For number 13, they are saying, this is the Serway book, Volume 1, 11th edition. Number 13, a rotating wheel requires 3 seconds to rotate 37 revolutions. Its angular velocity at the end of the 3-second interval is 98 radians per second. What is the constant angular acceleration in radians per second per second? So the rotating wheel requires 3 seconds to rotate 37 revolutions. Its angular velocity at the end of it, at the end of the 3-second interval, is 98 radians per second. What is the constant angular acceleration in radians per second? So they're giving you revolutions, and you guys go with radians somehow. So let's see what we got here. We remember that 1 revolution equals 360 degrees equals 2 pi radians. Well, the 2 pi radians and the 1 revolution set equal to each other will get us where we need to go. So, what we can say is 1 revolution, every revolution's got 2 pi radians. The conversion factor is 2 pi radians for every 1 revolution. I mean, you can flip it around the other way and also get it into the work. Okay, so let's see what we can say here. Essentially, there's a number of ways to play this. Let me see what I can say here. I would look at it in the sense of we want the acceleration. There's why I can tell you how much way to go here to make this thing happen. I tell you what, they're telling us that it's 37 revolutions. 37 revolutions. 2 pi radians for every revolution. 74 times pi radians is how much has happened. That's the see we got it. I mean, so when you basically say a whole bunch of things on this, kind of debating with myself, I kind of go off and give you a little break from the notes and show you how we look at it. But I think what I'm about to do is probably the best way to go. Theta is the average omega times t. What does that mean? Theta is omega f, the final omega, plus the initial omega, added to, divided by 2, and multiplied by t. So we have this right here. That's important. That's obviously important. Let's see what we can say here. Theta is 37 times 2 pi. 37 revolutions times 2 pi radians. That's why I got 74 pi radians. That's theta. They told us the omega f. Well, you got to make sure your units agree. If it's revolutions, you keep everything revolutions. If it's radians, you make everything into radians. The T is 3 seconds. Sounds good to me. The rest matters. The rest is, just so we have it here, those boxes of chalk we have somewhere, right? I left them up here. We'll find them. We don't need them now. We'll find them here. It's just something to keep in our back of our minds, I guess. They're gathered around somewhere, I'm sure. So we're here. We're fine pretty much. The rest is algebra. You figured out how to do it, the rest is algebra. Multiply by 20, do whatever you're going to do. Multiply by 20 side, divide by 3, subtract 98. You're basically solving this. How do you solve? You're going to multiply by 20 side. You're going to divide by 3 on each side. So multiply by 2 on each side. Divide by 3. Multiply by 2 on each side, divide by 3 on each side, and then subtract 98. Do all the algebra you have to do when you're working. That's 57 radians per second. That's the initial. The final, they gave to us up front. So, omega I is 7 radians per second, omega F is 98 radians per second. They want to know the angle. Now, they never asked me this, but if they did, you can find it. You just did. This is already good. This is what you found out. Is it true? Alpha. Remember the equations I did earlier, guys? You've got them in an earlier video. An earlier part of this video or earlier video itself, depending on how I formulated it. You guys have it. You have it in my lecture notes. This is omega F. The other one's omega I. $98, 57, over 3 seconds. 98 radians per second minus 57 radians per second divided by 3 seconds. Okay, let's get that a little bit better. On the order of 13.67 radians per second squared. That's 13. I think this is the one we're looking at, the way it was not going. So we're looking at this. That's 13. This is 17. What is the tangential acceleration of a bug on the rim of a 10-inch diameter disk if the disk accelerates uniformly from rest to an angular velocity of 78 revolutions per minute in 3 seconds? When the disk is at its final speed, what is the tangential velocity of the bug? That's A. Or that B, rather. 1 second after the bug starts from rest, what are its tangential acceleration, centrifugal acceleration, and total acceleration? All right, there's a lot there. Try to give you some, hopefully, decent drawing of what the heck's going on with this thing. We see, there's literally, the parts of the problem are A through E. We almost ran out of letters in the English alphabet at that point, guys. So we got a lot of stuff here. Let's look at 17 and try to get that idea of what they're talking about. I can say a lot. Let me try to, I've got it drawn a particular way in my notes. I have it drawn in a particular way in my notes, so maybe the fact that I repeat myself so much might actually help right now, because half the time the audio is not that great. So maybe on 2 tries, maybe you guys did. Here we're all maybe the class can deal with everything. You know, do this. All right, guys. Hang in there. Everybody's working hard to do this. It's just it's a tough situation. All right. So what we got here is 17. And like I said, the notes. Some people, I know a lot of people just go straight to the notes. The notes are very much out of heart. And those are seen and in no certain terms as we're seen. So I have any issue with it. Have one of them, the other, we'll figure this out. I'm going to do what I can for you guys to try to help you. We'll see how we can do that. We'll try to do it. All right. There's a lot going on here. Let's take a bird's eye view. Now we're kind of all over the place. There's one that you're looking right now, I'm going to say. And let's take a bird's eye view of the turntable or the disc. And they want to know if there's a bug on it, and you can figure out where it is, and. So we're going to figure out what's happening here, guys, and how the whole thing works. What's basically going on is, let's say there's a bug right here, guys. It's going around at a particular speed. Let me find out the tangential acceleration is this. Tangential acceleration is that. Okay, guys, I think I should make this a little smaller, make it easier to do this forgiving. Not highlight this, I'll highlight the other stuff later. Here's the bug, give you leisure to look at. There is some kind of acceleration, atangential. There is a centrifugal acceleration going inward. It's a little bit smaller. Not a big deal. I mean, that's not really a big deal here, guys. And you've got and that's the total. That's the grand total acceleration. And there's an angle. This whole thing is 90 degrees right here. This thing we can call theta in British. And this guy we can call phi. And phi plus theta is a 90 degree angle, which is equal to pi over 2 radians, which is equal to a quarter of a revolution. 1/4 of a revolution is 90 degrees. 90 degrees is pi over 2 radians. Depending on what language we're speaking here in mathematics, you guys, to make this thing a reality. It is what it is. So, that's something to kind of keep in the back of our minds as to what's going on. We'll keep this under control to find out what's happening here. Let's talk a little bit. Let's go bits and pieces with this thing and kind of make a little bit of sense. What is the tangential acceleration of the bug on the rim of a 10-inch diameter disc if the disc accelerates uniformly from rest with an angular velocity of 78 revolutions per minute in 3 seconds? That's it. Well, that's not that bad. It's only 78 revolutions per minute in 3 seconds. Simple as that. What's the tangential? What's going on? Well, that's the tangent speed. So the tangent speed is v omega r. The tangential acceleration make sure that we're speaking the right language here. But then, you know, there's a lot here. We said that alpha and A are connected. A equals alpha times R. Sounds good to me. Tell you what I'm going to do. The tangential acceleration. Tangential acceleration, in this case, A sub tangent, A sub t, is going to be what is it? Well, okay, now I got to be a little careful. This thing started from rest. Alpha R is what's going on here. So I'll tell you what you're going to do. Just trying to debate with myself how to explain this to you. Let's do this. You are going to go omega f minus omega I times R, the whole thing over t. Period. See what we got here. A sub t, the omega f is a reached 78 revolutions per minute. 78 revolutions is 78 times 2 pi radians. Every 2 pi radians is a revolution. 78 revolutions times 2 pi radians per revolution divided by 60 seconds, because it's 78 revolutions in a minute. So 78 revolutions is 78 revolutions times 2 pi radians per revolution divided by 60 seconds. It started from rest. The diameter, the 10-inch diameter disc, so it's 10 inches divided by 2, that's the radius. It got to this speed from 0 in 3 seconds. We have got to make the inches into meters, and then we're set. We don't have to. I can give you the answer in inches per second for the tangential acceleration. We don't have to. But they're asking for meters per second. So let's go. You're basically, I'll tell you what, let's take the inches here and make them into meters. There is 1 foot for every 12 inches, and every foot is 0.3048 meters. So what do we got here? We got this. For 3048 meters per foot. Feet cancel, inches cancel, the rest is math. Take this thing and do it. 0.346 meters per second squared. in a particular way. This guy does that, for this, you're essentially, you know, I draw this any way you want, guys, but you got, let's say the centrifugal is this. The tangent is that, and then you got this, and then you got angle. The angle between the two is phi. That's just kind of looking down the road, you guys. So let's. ATA. So you got this, you got this, you got that. Here's your phi. Here's AT, here's AC. I'm sorry I'm getting this thing at the ground back. A squared equals AC squared plus AT squared. Looking like that, we play all the gauge interplays. The tangent of phi is going to be AT over AC. Phi is going to be inverse tangent. I'm kind of getting ahead of the game here, guys. Why not? You know, et cetera, et cetera. So we're going to keep this in your mind. We're going to get to the next. B, they're asking you, what is the final speed at that point? After 3 seconds, when we reach that particular speed, there it is. BF equals, and like I said, we said, it's 78 revolutions per minute. That's 78 times 2 pi radians per minute. Per minute. And we know from all the mumbo jumbo we've done, 5-inch radius divided by 12 inches, so how many feet that is, and you multiply it by 0.30, 48. I'm the only person in the universe who runs out of blackboard space with a room about 50 meters wide. I know, so I know. Is that pretty much at the very, very end here? Okay. So we got it. We're looking okay here. All right. At the end of the day, you guys, again, they prefer things MKS system of units. Things are going to be explicitly said to you that will make things happen. That is B. Your answer. That's the speed of the enemy. B. C. Tangential acceleration is the same as, as earlier. So let's see what they did here. For some reason, I think that's because it's twice. I have no idea. What is the tangential acceleration? C. On 1 second after the bug starts to rest, what R is tangential acceleration? Okay, yeah, that's a good question. It's gonna be a relatively easy answer. May repeat myself more than I need to, but I want you to hear me when I say this to understand it. So, like I said, I personally, I can be wrong. I personally thought you all knew what it says. So, sometimes. at least in this room. So when we look at this, let me see what I can tell you. From 0 to 3 seconds, there's an acceleration taking place to bring this thing to this, to make this thing do what it does. For it to reach a particular speed, there's an acceleration taking place that brought it to this tangential speed. To bring it to this tangential speed, there's an acceleration that took place over a 3-second interval. That acceleration, what they told us, is a constant acceleration. So this is the tangential acceleration over that 3-second period of time, and it's constant. So it's the same acceleration after 1 second. After 0.1 seconds, it's still this tangential acceleration. After 0.7 seconds, it's still that tangential acceleration. So that doesn't change. The tangential acceleration tangential acceleration is the same as earlier for C. D, what's the centripetal acceleration? Centripetal acceleration, as we have said, is this. Capital R, I think I've been using small r, it won't matter. In this case, small r and capital R are the same. Let's not get caught up too much in the language. Either one's fine, we know what we're talking about, we agree with what we're talking about. B squared over R. A sub C equals B squared over R. That's equal to, well, did we say that omega times R, B is square it when it reaches that maximum speed. Omega times R is B, you square it, you got R here. You got omega squared, R squared, over R. A sub C is omega squared R. Yeah, that's definitely true. I haven't given you a final answer yet. But, there's a lot of ways to do it. So this is all true. Maybe we just stay here and we're fine. And now let me proceed to the clean and jerk aspect of the competition. I'm going to try to lift this. That actually was easy this time. Other times I don't know what I'm doing. Perhaps it's a technique that I'm acquiring. All right, guys. So, D, either one of these is going to go. It's going to be fine. Let's see what it is once it's done. Now look, the centripetal acceleration is changing during the acceleration. The acceleration is constant. But as this bug is being accelerated in the angular sense, the tangential speed increases. This is the AC is the tangential speed squared divided by R. So let's put the maximum tangential speed at that point. Or maybe they did. Let's see where they're asking for this one. What they're asking for this. See exactly what we're going to do here. Centripetal acceleration. I just want to make sure the rate. Just make sure we got this right. So what we have here. Okay, for some reason here. I'm almost wondering if this is actually tangential acceleration. We just try to think. Right, okay, this gets a little potentially moved up. What you're going to do for the tangential acceleration, you just see really quickly, guys, if I can do that. For some reason, I'm not believing the number I got here. So perhaps we've got to. Let me ask myself a question, guys. I don't want to proceed too heavily here regarding this. For some reason, I'm not quite believing what I'm getting here for an answer. I have it down here in the notes. I've got a feeling. I'm not believing my own notes right now on this one, guys. So let me please look at it. 1 second after the buck starts to rest, actually, this is one of the rare occasions I actually know what I'm talking about. It seems like I'm doing it right. So I actually do what I'm doing. So 1 second after the buck, 1 second after the buck starts to rest, what are his tangential acceleration? We got that. What is the centrifugal acceleration? The centrifugal acceleration, you guys, is going to be the tangential acceleration that's present. Tangential acceleration that's present times the amount of time it's taking to go from 0 to 1, which is 1 second. That is the speed. That's the speed after 1 second. After 1 second of that much tangential acceleration, we have a speed. The speed squared divided by the radius. The radius is 5 inches divided by 12 inches, that's how many feet it is, times 0.3048 meters per foot. It's a bit of a long song and dance, you guys, but at the end of all this, AC is 0.943. That's D. Now they're saying for E, and he's kind of a little bit all over the place. It's not bad. It's not as bad as I said. I think we already kind of did a lot to get E to work for us. That's it. That's D. So let's do 17E. Let me start erasing some stuff. Let me go up here, erase some stuff over here. And I think that we have access to these. And I tell you guys, this is a great lecture hall. I love it. I had you guys here in person. You love it. I mean, it's great. I just, like I said, the sound is something I'm a little concerned about, but other people told me it's pretty good, so perhaps you guys do better than I do. But like I said, we'll figure it out, and some great efforts to be made by everybody. So we're doing what we have to do to try to help everybody out, guys. I know you guys are going to be helping us out. I know it. We've got great treatments together. So with this in mind, let's go back to where we were. Let's get it together, let's figure this thing out. Where's this? Everything else up here, and this kind of tells us where you're going. It should be pretty straight. We did part E. We did part E already, so I mean, it's going to be looking at something like this, and this is really the argument, especially right here. This tells us a whole lot right here. And again, know the arguments that take place here, guys. Let's see what we can do. This is after 1 second. Well, I already said the tangential acceleration doesn't change. The tangential acceleration over that 3-second interval is constant. So after 1 second, it's constant compared to what it was in 3 seconds, compared to what it was in 2 seconds. The tangential acceleration does not change. Tangential acceleration does not change. The centrifugal acceleration is a particular value. And we know what it is. We did find out what, we already knew what AT was. We just found out what AC was at 1 second. The rest is the Pythagorean theorem to find this, some trigonometry to find this, and we're done. Remember now, it's pointing this way, or wherever it's pointing. These are the angles that we're talking about. Plug in all the numbers. And what we get here is kind of interesting matter. I mean, they're saying, take this. Take the square root of, okay, so here we go. Let's see. We got AC, we got AT. AC we're looking at something like this again. Write it out. A it's coming out to that. Theta AC, now, yeah, this is all right. AC divided by AT. Let's make sure we got this on the board, guys. In this regard, that should be the way I drew it. It's not really faithful to it. It should be F dash G theta. The notes, I labeled it wrong. The notes were not the right numbers. Watch out for that. Just watch out. I mean, this is AC. This is AT. You know, it's not a big deal, but it's a big enough deal. Okay, it's theta. Actually, we have to big way. 69.8 degrees below tangent to circle. That's it. It's as simple as that, you guys. 68 extending the fine out over here. And that's about right. It actually accidentally is drawn to a really good scale, so we're looking pretty good. So this is it. This is what theta is. And this is the magnitude of the total acceleration. You almost wonder if they planned it that way to make the whole thing total to 1. You know, how do you do all that stuff? Whatever. It looks pretty good. So it's on the mark now. Basically, you do a bunch of things here. You got to do it in mil, so it's 1.00 meters per second squared. At theta equals 69.8 degrees. 20 degrees, a little tangent circle. So, what we have here, we're okay for the chalk so far. I'm just looking over here. Looks like we got a 10 number here. So that's interesting. Let's see here.
I can get you some more.
I think we're okay right now. We had a lot of it. We'll figure it out. We're okay so far. So we got this. We got this right here, you guys. If you wanted to write it in terms of phi, A vector would be 1.00 meters per second squared. That ain't changing. At phi is this guy. And that's AT divided by AC. That's AT divided by AC is the tangent of phi. The inverse of phi, well, it's also the complement of what theta is. If this is 69.8, the other one is 20.2. At phi equals 20.2 degrees with respect to radian. And there it is. One of these are the real complementary angles. If this is nearly 70, this is going to be nearly 20. If this is about 70, that's about 20, because they add up to 90. So it's looking pretty good that way, guys. That's 17. Let's go to 39. All of this is in Canvas, word for word. So if you're having a hard time hearing me, or if you don't want to look at my face, like most people don't, then go to Canvas, and it's all there. Okay? It's all there, what I'm doing. Okay. 13, 17, let's go to 39. Projectile is fired straight upward from the Earth's surface to the South Pole with an initial speed equal to 1/3 the escape speed. A and B, ignoring air resistance, determine how far from the center of the Earth the projectile travels before stopping momentarily. What is the altitude of the projectile at this instant? We're saying that the projectile gets fired straight upward from the Earth's surface at the South Pole with an initial speed equal to 1/3 the escape speed, you guys. A and B tell us ignoring air resistance. A and B asks us, ignoring air resistance, determine how far from the center of the Earth the projectile travels before stopping momentarily. What's the altitude of the projectile that is? They're all kind of one of the same. The question's sort of one of the same. Well, let's take a look at it. when the kinetic energy is done. So, some stuff that goes on, a little rough to talk about sometimes, in some of these regards. Let me try to. That's exactly how I'll talk about it. I think it's easier than it can be made, I guess you could say. You gotta find out what the escape velocity is. There's a formula in the book that tells you. I'm gonna say this. I'm not sure this is the best way to do it. The notes are there. As I said, they're ever present, guys. R equals RE, the radius of the Earth. The radius of the Earth is going to be R. For our purposes right now, the V escape from the surface of the Earth divided by 3 is how fast it's firing. Well, the escape velocity from the Earth is given to us by this. This guy and this guy are the same. You want to divide by 3? Yeah, get over there. I get over here. So there we go. So let me see what I can say here. The total energy of the system is a constant. Thank you. Christine just threw them at me. I'll go tennis and baseball. No, thanks. I was joking. All right. So I think we're set, guys. I'm going to go with my writing style, use my last another 2 minutes. Let's see what happens. All right, so we got all this. How are we doing? Okay, we got to here yet. That's that. We also want to talk about a couple things. We want to say, how about the kinetic energy at any particular instant plus the potential energy at any potential, the kinetic energy and potential energy at any particular instant, they add them together is equal to the energy, E, and that's a constant. All right, you might say, so what? Well, here's the object, mass M. V squared is this. Now here's where it gets odd. I'm going into this too much with you guys, perhaps I can do it some other time in a different context. Right now we're here, we're in the dance, we got a dance. We've got G is G, mass of the Earth, M over R. This is the potential energy at a distance R, any distance R. In this case, from the center of the Earth is how you measure radius, small r. From the center of the Earth to the surface is the radius of the Earth. They put a negative here because it's a weird bookkeeping, man. And every time I discuss it, this is where I really wish I had everybody right in front of me, so we can talk about it a little bit more. But let's just make a long story short. The highest potential energy, according to this negative scheme right here, the highest potential energy is the highest potential energy in this scheme is 0. The lowest potential energy is toward negative infinity. It's odd, it's an odd bookkeeping method, but when you do subtractions and comparisons, it actually works out pretty well. It's a rough one to call. In other words, let's put it this way: the biggest number you can possibly be given in a particular argument, in a a particular system, in a particular mathematical experiment, if the biggest number is 0, that means all other numbers are negative numbers. They're claiming the highest potential you can get is 0. And that happens in a approach that when you go infinitely far away from the surface of the Earth, the center. The closer you get toward the center, the less potential energy is going to be present. So, here you are. Anyway, that's the cookie. It does work. Hopefully it'll make a little bit of sense in a little bit of time. They're making this claim. And we are saying, what's 1/2 mv squared? Well, trying to think pretty good on this one. Okay, here we go. If this is the velocity under consideration, if you take v and square it, you're also taking this, all of this, and squaring it. When you square this, you get 2g me over re over 9. You get 2g me over re over 9. The 2's cancel right here. This guy, I tell you, the RE is here, so you can put the RE down here and not have it be there. And not have it be there. Let's get a 9 RE down here. Let's multiply the bottom by 9. Let's multiply the top by 9. Okay, what do we got here? What we have we've got all this right here. What do we got? The total energy of the system, no matter where you are in the system, is going to be 1 GME over 9 RE plus, let's see here, for some reason, there should have been an M here, guys. There's an M right here, the capital M somewhere else. That's the least of my concerns here. When I'm doing this, we got this right here. We've got the other one right here, the -9 over small m right here. So there's a small m present. I was right here. Gotta have that right here. All right, so we are right here. Guys, G capital M-E, small m over 9 RE. G capital M-E, M over 9 RE. Both cases. You got this guy on the -9. You got the same guy on the +1. When you multiply them out, you get -8 over 9. GME M over RE. Depends how you write it. That's the way they wrote it there. Well, that's the way I wrote it in the note. I'm referring to myself in a plural third person. This is ridiculous, right? That's how they wrote it. No, they is me, and I wrote it, so there it is. So we got this. Okay, it's looking okay. This is constant for these circumstances. At very top, there's no KE, it's all PE. draw the light this in. When this thing goes to the very top, what does that mean? At the very top, it's all potential energy. Well, the potential energy at the very top is negative GMEM over our mass. Our mass, I want to make that very clear. Our mass is equal to RE plus H mass. Basically, R is going to be RE plus some kind of H. And when you're talking about the mass, you're talking about this. That right there, when it's at the very height of its journey, there's no kinetic energy. It's all this. It's all potential energy. All this potential energy equals the total energy of the system. So these negatives, as disturbing as they are, I've been teaching this for a long time, and I'm not thrilled by it. But I can tell you they're a good bookkeeping method. Are there other ways you can probably handle this? Yeah, I think so. Yeah, definitely. I think there are. How you want to do it is, like I said, there's a different arbitrary nature to it. But this is it. This is huge. This is huge. So get you where you want to go. What do you mean? Well, how about divide by capital M-E on each side. Divide by small m on each side. Divide by G on each side. Put a negative 1 right there. Pretty good to me. Take this out again. What do you got? Got it. Yeah, the negative is not a big deal. It's going to fall out of it. Multiply by negative 1 on the side. Multiply by negative 1 on the side. And flip them both upside down. If two things are equal, the reciprocals are equal. Multiply by negative 1 on each side, get the reciprocal on each side. Our mass from the center of the earth is this. The maximum height is RE plus H max. H max from the surface is R max minus RE. That's this one. So here we go. Let's see what we got. So it's saying here, the R max is the radius of the Earth is 6.38 times 10 to the 6 meters. It's about 6,380 kilometers is the radius of the Earth. That's 6,380,000 meters. 6.38 times 10 to the 6 meters times 9 over 8. This is our mass. So there it is. That's our mass. 8 times 10 to the 5th, or about 7.98 times 10. That's what your calculator is doing, guys. We're not going to make no diamonds too much. We're trying to make it so reasonable, but still, you got to have a degree of specificity. Don't get that wrong either. I subtracted from 7,180,000 meters, there were 700, the R max from the center of the Earth to the apex of the journey. Center of the Earth to the apex of the journey. R max is 7.18 times 10 to the 6 meters. That's our max. I'm going to subtract RE, which is 6.38 times 10 to the 6 meters. It's 0.8 times 10 to the 6 meters. That's 800,000 meters. I think I was doing more specificity in the calculations. So that's A, and this is B. Let's look pretty good together. That's 39. 44. A 600 kilogram satellite is in circular orbit about Earth at a height above Earth equal to the Earth's mean radius. So it's above. So a 600 kilogram satellite, for number 44, a 600 kilogram satellite is in circular orbit about Earth at a height above Earth equal to Earth's mean radius. Find A, the satellite's orbital speed. B, the period of its revolution. C, the gravitational force acting on it. So A, B, C, pretty neat stuff. You're going to find the satellite's orbital speed, its tangential speed, so to speak. You're going to find the period of its revolution. How long does it take to go all the way around the Earth? C, the gravitational force acting on it. Sounds good to me. Let's see exactly how we're going to do that. They are telling you, I'm going to make this very clear, guys. It's in a circular orbit about Earth at a height above Earth equal to Earth's mean radius. What does that mean? That means, is that pretty legible? Now, I can say, I'll go if this is the Earth, let's see what I'm using. If this is the Earth, and this is the radius of the Earth, this is the center of the Earth, this thing is up higher from the surface. Another RE. The height is RE. The distance, R or small r, whatever you want to call it, the total distance here is R. That's 2RE. Or if you want to call it capital R, then it's still 2RE. So, see what we can do. This is what we're talking about, 44. The math should be pretty straight together on this one. Just make sure understood what we've done here. Here's our E. Here's our E. Here's another R. For 44. Bring this down, we'll proceed and come back. let's see what we can say here. Exactly how I proceeded to do this. Try to think about where we're going to go. Okay. I got this in the notes. I want to make sure you're okay with the notes. Okay. If this guy is in orbit, just trying to piece this together a little bit. Okay. I think we got this. Here's where you want to go. The force centripetal. Remember, we did this when we were talking about a gut feeling derivation of Kepler's third law, when we talked about the period. Remember how we did something like T squared, look at it. Some constant times e to the third, or T squared, if A is just the average radius. Something like this, and there's a lot we can do with this, and we'll cross every bridge we have to do it. We did that by saying this. Force centripetal equals the force of gravity. What does that mean? Well, what's the radial distance to the height? We just said the height is our we said the height, not the height. Take that back. Height is RE. Height is RE. RE equals RE is this radius. Is the radius. Radius is 2RE. Tell you what, centripetal forces, here's your satellite, 600 kilograms. It's going to be squared divided by 2RE. 2RE is the R. Remember, F centripetal is mv squared over small r, or r in general. Mv squared over r is F centripetal. The r is 2RE. Mv squared over 2RE is the centripetal force. The force of gravity, G M over the radius squared. That's it. That's kind of, this is the basis of everything you're going to do on this thing. This is the basis of everything that you're going to do on this. So, play the game. They want to know how fast it's going. You want to know how fast it's going? Tell you what, just solve the beat. Do the math and solve the beat. It's as simple as that. You got E squared. Why don't you multiply by 2RE on each side and divide by small f. And it's that. Square root both sides. Simple as that. Let's put the numbers, guys. G is 6.67 times 10 to the negative 11, the appropriate units. The mass of the Earth is 5.98 times 10 to the 24 kilograms. 2 is 2. The radius of the Earth is 6.38 times 10 to the 6 meters. Put all the numbers in there, get an answer, square root the answer, and have to be it. How fast is that thing going for this to be working? Tangential speed. That's it. What's the period? So that's it. I mean, we got here, Yeah. I got an idea. Is it true that V is 2 pi times R over the period? Yeah, it's true. Why don't you multiply by big T on each side and divide by V? Got more news for you. That small r is the radius, capital RE plus capital RE, added together. Capital RE plus capital RE is what that guy is. T is equal to 2 pi 2 RE over V. That's it. That's it. T is equal to 2 times 2 is 4 pi RE over V. What's that? 4 is 4, pi is pi, RE is 6.38 times 10 to the 6th. V is 5,591. Plug everything in there. And you get 14,339.74 seconds. How do you convert that to minutes? How do you convert that to hours? How do you convert that to days? How do you convert that to years? How do you convert that to decades or centuries or millennia? It's all math. It's all pretty easy. Tell you what, the reasonable one here is probably this 14,339.74 seconds. Probably the easiest one would be here. Take that and divide it by 3,600 seconds. Every hour is 3,600 seconds. When you do that, so that's fine, depends on asking the question. Almost 4 hours. It's going to go around the Earth once every 4 hours. T equals 3.98. T equals 3.98 hours, which is the same as 14,000. T equals 14,339.74 seconds, which is the same as saying T is equal to 3.98 hours. So, there's V, there's A. We're looking pretty good here. Looks pretty good. Let's go to 51. An athlete swings a 5-kilogram ball horizontally on the end of the rope. The ball moves in a circle of radius 0.800 meters at an angular speed of 0.5 revolutions per second. What are the tangential speed of the ball? Its centrifugal acceleration, its maximum tension, rope can withstand before breaking, is its maximum tension. The maximum tension the rope can withstand before breaking is 100 newtons. What is the maximum tangential speed the ball can have in newtons? All right, guys. It's kind of a loaded statement here. Potential. The athlete swings the ball horizontally. The whole procedure here forgive me, for 44 we're not quite done. There's a C on that. Forgive me, guys, there's a C on that. For C, they're saying, what is the force of gravity on the object? Forgive me. So the force of gravity on the object is going to be G M-E M over R squared. Now we already said G ME M over the small r squared is 2RE squared. That should be what, right? That's okay, right? Okay. That's all we're saying. So what are you going to do? You can do everything you did in the past. This is, the G is 6.67 times 10 to the negative 3. Negative 11. G is 6.67 times 10 to the negative 11. ME is 5.98 times 10 to the 24. The mass of the satellite is 600 kilograms. So 600, say it's 6 times 10 to the 2. Over 2 times RE, the quantity squared. 2 times the quantity, 6.38 times 10 to the 6. Get an answer, square it. That whole bottom answer is divided into here. All right. Throw all the numbers in there, you guys. And what's the force of gravity on this thing? Do the mathematics. I have it all written down for you on D12. Forgive me, on Canvas. 14.69. Sorry, 1,469.9 meters. 1,469.9 meters for that. That was, sorry, had to finish that out. So it's ABC for number 44. For 55, they didn't tell us something, and when they don't tell you something, I think it's fair to assume that you don't have to worry about it. And that's not always the case. I'm not going to be explicit with you. But there's that thing I already talked to you guys about this in the past. There's that philosopher Occam, and they say Occam's razor, which means you sort of go for the easiest assumption that's present, and that is reasonable. It's got to be reasonable, and it's got to be, usually the easiest way to look at it and is reasonable, not something outrageous. It's a reasonable assumption you do. We are not assuming that gravity is affecting anything here. You could almost say it's on a frictionless surface, it's being rolled around on a frictionless surface, so gravity really wouldn't have any play in this. Or you could say the person's in outer space and we're rolling it around, and gravity's not affecting it. The only force that's really happening here is the centrifugal force. You want to look at things along those lines. So, because that's the assumption they made here today. So let's take a look. Say, basically, I told you what we're going to say here. An athlete swings a 5-kilogram ball horizontally on the end of a rope. We're going to say there's no gravity here, it's all going to be centrifugal force. That's Occam's razor that we're going to use right now. An athlete swings a 5-kilogram ball horizontally on the end of a rope. The ball moves in a circle of radius 0.800 meters at an angular speed of 0.5 revolutions per second. What are A, B, C? What are they? What is the A? What is the tangential speed of the ball? B is the centrifugal acceleration. If the maximum tension that the rope can stand before breaking is 100 newtons, what is the maximum tangential speed this thing can have? It should be that. The tangent, V tangent, is omega times r. V tangent is omega times r. What does that mean? Well, omega is 0.5 revolutions per second. Yeah, 0.5 revolutions per second. Huh? And there's 2 pi radians in every 1 revolution. And the radius is 0.8 meters. So let's write that down over here, a little more meaningful. There's 0.5 revolutions every second. There's 2 pi radians. There's 0.5 revolutions every second. There's 2 pi radians in every revolution. And the radius of the circle is 0.8. Comes out to 0.85 meters per second. Come out to about 2.51 meters per second. This is pretty, this legend up here. It's pretty legible up here. Okay. I think it's good. I think we're okay, guys. So that's it. We can kind of make a long story short on that one. VT, as we said, was the omega times R, and omega was 0.5 revolutions per second. Every revolution got 2 pi radians in it, and the radius was 0.8 meters, and multiply all up, the right conversions in there. And we are talking about, given the circumstances that they've outlined for us, this is what we have. This is what we have. B, what's the centrifugal acceleration given those circumstances? AC, the centrifugal acceleration, is V squared it's the tangential velocity squared divided by r. Small r, big r, whatever. Maybe stuff gets used interchangeably a little bit. We're doing. Let's make sure you know what we're doing. That's the big thing. We know just from the record that omega times r is V. V squared is the quantity of omega r squared. V squared is the quantity of omega r squared. We got this. We know this. Not that it depends where you want to go with this. Not even want to go with this. Okay. But all of this is true. Look, we're not going to make a big deal out of these guys. We play this a whole bunch of them. We can take this guy, the tangential, just take the V, which is 2.51 meters per second. We will square that quantity and divide it by, so V squared is 2.51 squared, divided by 0.8. And wherever that goes, it goes. Looks pretty good. Looks pretty good. So, what do they say? Well, we got that. When does this thing break? Tell you what we're going to do. You know that's true. If you know that's true, the rest is math. Give me the velocity where this thing's going to break. Tell you what we're going to do. Let's find a maximum. let's go. Let's plug everything in. Let's get B by itself. Tell you what, B squared is equal to RFC over M. B is equal to RFC over M square root. Talk to me. The radius is 0.8 meters. The maximum tension force is the maximum centrifugal force that can be given to it. Beyond the maximum tension, you're going to break it. It ain't going to work. The maximum centrifugal force that you can give to it is the maximum tension force that it can withstand. The tension force and the centrifugal force are one and the same. 0.8 meters is R. 100 newtons is the maximum centrifugal force, which is the maximum tension. And the mass of the object, we're told, is 5 kilograms. Correct. 0.8, 100, 5. Do the math. The most you're going to get this thing to go at, and not break it, not break the string, not break the rope. B is equal to 4 meters per second. That's it. That's 51. Let's go to 53. The solar maximum, for number 53, the solar maximum mission satellite was placed in a circular orbit about 150 miles above Earth. Determine A, the orbital speed of the satellite. B, the time required for one complete revolution. Okay. Quite similar to what we've done. Let's be careful. We're okay. All right, let's see what we can say here. 53. I guess it's, I'll look at this, I think it's easier now. I'm probably about to make it, so let me make it pretty easy here. Let's say that I'm using different rotation. I know I use small r somewhere. Let's use capital R. Capital R is the distance from the center. H is the height above the surface of the Earth. And then from the surface of the Earth to the center is RE. So RE plus H will give you the total distance from the center of the Earth. Let's do a couple things. They said this satellite was put into orbit about 150 miles above the surface of the Earth. 150 miles. Each mile is about 1,609 meters. Plus 6.38 times 10 to the 6 meters is the radius of the Earth. This is the radius of the Earth. This is H. I think we're looking pretty good. We go here. $6,621,350 meters. the center of the earth to the 150-mile height from the surface of the earth. 150 miles from the surface of the earth to where it's orbiting. 150 miles from the surface to where it's orbiting. 150 miles. And 6,380,000 meters from the center to the surface. And together, that's the total distance from the center to the orbital height. That's the total distance from the center to the orbital height. You guys remember, we just did it. mv squared over r is the centrifugal force. M over r squared is the force of gravity. We use this reality to derive Kepler's law. To derive Kepler's third law, we use this reality. The last time we were together. So it's looking like this. What do you want to do? I want to do what we always do, guys. Let's multiply by capital. Let's multiply by capital R. Let's multiply by capital R on each side and divide by small m. It's looking familiar. It's looking like this. Square root each side. I think it looks good. Looks right here. Plug in everything you got to plug in there. G is 6.67 times 10 to the negative 11. ME is 5.98 times 10 to the positive 24. R, we already did that little song dance over here. Big R is 6,621,350 meters, which is 6.621. 35 times 10 to the times 10 to the 6 meters. So if you plug in all the numbers, plug in what G is, plug in what ME is, plug in the R that we just discovered over there, we find out what it is. Go for it, let's see what we got. 7,762 meters per second.
Excuse me.
Yeah.
Could you stay right there? I have to let somebody in. I'll be
No problem. That's all. Just this big one right here.
And you can go up above too.
Okay, very good.
I'm sorry.
Very good.
Steve just called me.
Not a problem. We got it. Okay, so this is the way it is. The way I wrote this equation, the equal sign, I try to make it more clear and make it less clear than that sometimes. V is equal to 7,762 meters per second. That's it. It's about as simple as that. So let's see. Got this. That was pretty good. That was A. This thing's moving pretty fast, you guys. It's not a joke. This thing's moving, a little bit less than 5. This guy's going about 4.5 to 5 miles per second. 4.5 to 5 miles per second. Go up. Close, 7.7, 7.8 kilometers per second. 4.5 to 5 miles per second. It's going fast. Well, if it's going that fast, I'm guessing it's going to cover a lot of ground. Let's have a look at it. So, 53B there's a lot of ways to play this too. We've already done this, guys. Don't think it's surprised on that. We know V is 2 pi R. 2 pi pi r over capital T. Let's play the math. We've been there, done that. We have this right here. We have this. So I think we're good. I think we're good, guys. The only thing we're going to do now is what just happened here. Well, we already know that capital R is 6.62135 times 10 to the 6 meters. That's capital R. Pi is pi, 2 is 2, and V is 7,762 meters per second. Plug in all the appropriate values you got. You got 5,359.6. 5,359.6 seconds. Okay. Hours are probably a good way to go now. You kind of just look at it, not a big number. Tell you what, is there no way to make it? Oh, yeah, I got it in seconds. Let's see what we're right now. 5,359.6 seconds. Every time you got let's write in minutes, right? Every time you got 60 seconds, every time 60 goes in here, every time 60 seconds goes in here, you got a minute. This is 89.3 minutes. What's that equal? Well, it's 1 hour and 29.3 minutes. 1 hour and 29.3 minutes is about 1.5 hours. So you can, I'm not going to beat this thing up a little bit. 1 hour, 29.3 minutes. Seconds is the same as 89.3 minutes. It's the same as 1 hour, 29.3 minutes. That's about an hour and a half. So there you go. Christine's okay. Let's stay right on this slide, right? Okay. So we're looking good again. Let's talk about 71, 75. Yeah, there's a good amount of this one. It's a good one. I mean, there's another one I may want to do at some point. Maybe not. We'll see about that. Let's just see here. There's a good amount here for these last two. Let's see how we're going to do it. For 71 and 75, or as patiently do it, I'll try to show you some tricks on how to look at it. And I think we're going to be okay. All right, this is a pretty great problem. Let's carefully look at it. I've got it in the notes, so again, if you're going to have a hard time hearing it or something, don't worry about it. It's completely in the notes. Look at it that way. Always look at it that way, guys. If something falls short for you regarding what I'm trying to do here, don't worry about it. Go to the canvas, and I got the same stuff written on there. It's always kind of our safety valve. It's always our safety. It's always our safety in a sense to look at it. You always look at the writing, and it's there for you. So. So 71, what is going on here? Problem number 71 is a good problem, and we're going to talk about it. For problem number 71, the luggage carousel, there, I'm going to draw this and we'll figure it out as well. But for problem number 71, a luggage carousel at an airport has the form of a section of a large cone, steadily rotating about its vertical axis. Its metallic surface slopes downward toward the outside. This is interesting. It doesn't slope toward the inside. There's no point of a carousel if the luggage goes to the middle of it. You have to climb the carousel to get the luggage, right? So obviously it's sloping outward, the luggage carousel is going out. So let's see what we got here. Let's see how we're going to talk about it. 71, and they got how many parts to it? Just A and B, but it's loaded up pretty good here. 71, A luggage carousel at an airport has the form of a section of a large cone, steadily rotating about its vertical axis. Its metallic surface slopes downward toward the outside, making an angle of 20 degrees from the horizontal. A 30 kilogram piece of luggage is placed on the carousel, 7.46 meters from the axis of rotation. The travel bag goes around once at 38 seconds. In 38 seconds. Calculate the force of static friction between the bag and the carousel. B. The drive motor is shifted to turn the carousel at a higher rate of rotation, and the piece of luggage is moved to a position 7.94 meters from the axis of rotation. The bag is on the verge of slipping as it goes around once every 34 seconds now. Not 38 seconds now, it's 34 seconds. Calculating the coefficient of static friction between the bag and the carousel is barely be able to work again. It's a lot going on. I'll try to give you some feeling for what's happening. There are numerous arguments that work regarding this matter. There are numerous ways in which this works that I can explain to you. And there's two major arguments to make that really work well. I'm going to give you more of a gut feeling argument. I'm going to use a fictitious force known as the centrifugal force. When I'm driving a car, or somebody else driving a car, they take a sharp turn, and they're turning towards where they are, I feel like I'm about to fly out of the car. I'm really not. What the car is doing is yanking me in a circle. The car's acting like a rope, making me stay in the circle. However, relative to the car, it sure feels like I'm going to fly out of the car. And I probably should not be thinking otherwise. So that's where the made-up centrifugal force comes in there. You can pretend there's an outward tendency, and mathematically it's a really good ploy, and it's a really intuitive argument. It's something very intuitive when you look at it. All right, there's a lot going on here. There is a carousel. It's got a 20-degree angle horizontal, so it can be 20 degrees right here, and it's 20 degrees right here. That's it. The carousel rotates this way. The luggage drops that way. You're over here, you're over there. The luggage drops this way. This guy's rotating that way. There is alternate interior angles. That's transversal. Here's a line, here's a line. These are two parallel lines. Here's a line, here's a line, here's a line. Two parallel lines cut by transversal. Here's 20. So we got there's a lot going on here. We know that the magnitude of velocity is the circumference divided by the period. It's of interest. They gave us the radius, they gave us the period, the rest is something we can figure out pretty easily. There is an object right here, a suitcase. Later on, the suitcase, you guys, the suitcase is going to drop down lower. It's going to be a bigger distance away. But this is the distance R to get there. That's the distance R. And that's this R. That's this R right here. There is the weight of the object, which is mg. There is this guy doing this, and this guy doing that, and this is also theta equals 20 degrees. This is mg sine theta. This is mg cosine theta. So it's doing this. Doing this. There is a lot going on here. So let's be careful. There has got to be a frictional force. So I think a good way to say it. There's got to be a frictional force going this way. Why? Because I want the suitcase to stay there. The suitcase is in two different places. It's here, and later on when we speed it up, it slides down a bit. So it's going to be, but this is the general look of possible look. We know there is so we got this guy, friction going this way. There's a general slide down tendency, all in the aggregate, I should say, Fx. This and this are equal to nobody's movement. Here's what we gotta watch out. There is a tendency. We know the centrifugal force points inward, but there is a tendency. If I'm in the car and you take a sharp turn, I get thrown against the side of the door, and I hope the door is locked, and I hope my seatbelt is good. It's not that there's a force throwing me out of the car. It's the car itself grabbing me and keeping me in a circle. But relative to the car, if the car wasn't holding me, I'd be outside of the car relative to the car. So there's the fictitious force of the centrifugal force. Kind of use good mathematical way. I have other notes where I use this technique and the other technique where I use the centrifugal force, which is strictly the way that it works. The mathematics is strikingly identical. It is absolutely identical in both instances. Tell you what we're going to do. You agree there is a tendency to spun around like this to want to fly off. Remember, there's no car door holding on to me, so there's still a tendency to want to fly off. This is that. This is 20 degrees also. This right here is FC. F centrifugal. F centrifugal. Its magnitude is the same. You mind if I take this guy and go this way, and take this guy and go down? I'm going to make it. This is 20 degrees. This is 70 degrees. This is 20 degrees again. If this is FC, this is FC cosine 20 degrees. This is FC sine 20 degrees. This guy right here, we'll call him FCY. Hold it. This guy right here, we'll call him FCX. So a lot going on here. The notes are probably a little easier for you to handle if you go to Canvas. They're here too. Okay, I mean, there's a lot being said here. This guy's clarity, there's a tendency this way, and there's a tendency that way. Yeah, I need your help here, guys. What do you got? I'll kind of make a long story short. This is not flowing through there. We can say that F is equal to Fx. This guy right here and this guy right there, balance. Nobody's moving in both scenarios. This is FCX, as we said. This is FCY. FCY is this. FCX is this. And this is FC. Tell you what we'll do. What does your gut tell you? If this thing being spun around like this guy is not going to feel as heavy on the ramp as much as he would if the ramp was standing still. The fact that the ramp is moving around, this guy wants to fly off the ramp. There's this tendency to fly off, there's this tendency to slide down from the FC. So it's not as heavy as it was. If mg cosine theta is the downward rate, and it's made, if mg cosine theta is the downward rate, and it's made lighter by this amount, FC sine theta, the difference between the two should be normal. Let's talk. F equals ms times the normal. What is that normal? The normal is, what is the apparent weight that's on this guy? That's what's the normal that's equal out. Well, here's the apparent weight, you guys, mg cosine 20 degrees. mg cosine 20 degrees, here's mg cosine 20 degrees. That's the apparent weight. Yeah, as this thing is spinning around, this guy's tending to fly off. He's tending to fly upward by this amount, FC sine 20 degrees. So this is what it would weigh standing still, and this is what it weighs when it's not standing still. mg cosine 20 degrees minus FC sine 20 degrees. So what happens is, you end up getting, what's the normal? The normal is what it would be if everybody's still. Yeah, but it's apparent weight ain't as much. So you're there. Apparent weight ain't as much. What does that mean? That means at the end of the day, that F is ms mg cosine theta. We know what cosine theta is. This is what agrees with this. FC, what is the centripetal force? Ladies and gentlemen, work with the other R small. That's that. FCX was mv squared over r. The x was the cosine in this case. And the other one, the y, FCY, is mv squared over r sine. All right. We got him. They both came from here. And that's this guy The apparent weight makes the whole thing happen. This thing apparently weighs less. If it was standing on a scale, the scale would be a smaller number by this amount. Because it's being rolled around, it's being made to weigh less. Okay? So that's that. Okay. We said that, we got that. What's FX? FX is the slide down tendency. Ladies and gentlemen, I got two of them right here. I got this guy wanting to slide down. The X component of FC, and the slide down component of the weight. That's it. FCX. I'm using small R or big R. Really, man, they use, I use big R accidentally. Let me change small R to big R. That's not a problem. It's the same. It means the same thing. When you try to say, but in case you get in trouble with all of the canvas, I don't see that this is going to be a big problem for you. But here I put small R, probably big R. Even though the notes I put small R. Well, there's going to be some inconsistencies, guys, but the math is straight on the mark. So you got what you got, guys. And let's see what we do have. We got this. Need that into an R. This guy is mv squared over R cosine theta plus the slide down guy, which is mg sine theta. Guys, I don't think it's clear. We did say this. Now we're going to set equal. We're going to set this equal to that and see what we can do. That's all it is. It's the hard part of the whole thing. We do it. They gave us some stuff here. So let's see. They started out. I mean, there's just a whole bunch of ways to go, that's for sure. Let's kind of leave this. I'm still use this later on. Let me try to make this easier. What we can say is V is going to be 2 pi R, and the R that they gave us initially in this process is 7.46. Over the time, and the time that I didn't put in my notes, I just flat out did it, it's 38 seconds. It's all this. So at the end of the day, in the first scenario, for scenario A, for part A, is 1.233. That's B. So I'm gonna, guys, they're asking here, I mean, the problem, they want to know what the force of friction is that's making this thing happen. And that's, that's an interesting problem to total, right? I mean, it's not that bad. I'll tell you what we're going to do. When I go to B, I got to equate these two guys because they are equal. They are equal. I got to equate these two guys. They just want to know, if they're equal, I can go here and solve for fx. I can solve for capital Fx right here, which is equal to small f. Or I can solve for small f, it's the same as capital F. It doesn't matter. Use one or the other. they never gave me the coefficient of static friction. So the options, you know, I stand somewhat corrected, guys. The options, I can tell you that the options become a little more limited. I don't know what this is, but I can find that out some other time. I can find that out. In fact, I can find it out right now. I don't need to find out for A, but I gotta find out for B. And I'm gonna do that by setting these two. In the meantime, since they're equal, go up here. They're not asking for something that you don't have. Here I don't have this, and I can solve for it. I actually find out what it is when I equate these two. Because I know everything else. Let's go right here. The mass of this thing is 30 kilograms. The mass of the suitcase under consideration is 30 kilograms. It is moving at 1.233 meters per second. I will take that 1.233 meters per second, square it. I'll multiply it by 30 kilograms. I'll divide by 9.46 meters. I'll multiply by both sides of 20 degrees. I will add 30 kilograms times 9.8 times the sine of 20 degrees. When I do that, I know what fx is. Yeah, I know. It's the same as fx is the same as small f. When you grind it out, you guys, the force of friction holding this guy up is 106.3 newtons. I have another problem that I've given to you guys on Canvas called the suitcase problem. That's just about identical to this. Little bit different. That one you probably have to read. I don't know if I'm going to have time to get into that, given some of the time constraints I'm running. But and probably you need to. I mean, you've got it on Canvas. You can look at it and see what it is. So this is this one right here. Is this pretty clear? Up here, okay. So this is A. They are now asking you what I was asking you. What is F? What is MS? What is US? Well, I'll tell you what. Why don't you set these two equal to each other and do some math, and you'll find out what the US is. Now the US here is a little different. Potentially even the same. Yeah, it depends how they formulated this problem. It really depends how they formulated this problem, guys. I don't know if that's a can of worms I'm over right now. But let's see what we can see. They're saying for 71B, the drive motor is shifted to turn the carousel at a higher constant rate of rotation, and a piece of luggage is bumped to a position of 7.94 meters to the axis of rotation. The bag is on the verge of slipping as it goes around once every 34 seconds. Just barely. Calculate the coefficient of static friction between the bag and the carousel in this case. All right, guys. I'm going to now. I want you guys to kind of okay. We did what we did. It's up here. We got a record of it. May I look at a different situation? So the different situation is we're going to do something like this. Let's get another B. Another B. What are you talking about? Well, they gave me a different scenario. They say the thing got bumped to a place further away. So what's going on here? First of all, it's going around faster now. It's 34 seconds. The new R that's asked is 7.94. It's almost half a meter further away. It's 0.48 meters further away than it was before. 7.94 meters, and it's going at 34 seconds to go all the way around. It used to be 38, it used to be 7.46. Now it's 7.94, and it's not doing 38 seconds per period, 34 seconds. line for B and see where it's at. I don't know if I actually did put it up there. We did it, it came out to 1.47. That's different from 1.233, isn't it? The other one was 1.233 meters per second. This is 1.47 meters per second. That's for B. This is for B. That's the speed it's going. Okay, keep that in mind, and let's get down to business when we do this thing. I need to find what to do is, I think I know what up. That thing's getting higher, I'm getting shorter. I don't know why. I gotta get my feet over that. So, okay, we got this. And we got 71 B. Let's go. I'm going to set small f equal to big Fx. And then I'm going to solve for mu. Here it goes. Small f is mu x, mg. You can do this with any data. They have to give me this data, so they let me off the hook. Equals stuff not really hard, man. It's tedious and one mistake and you're done. So, US is going to be this. It's more aesthetic, I guess, if you don't put a set number in there, you put a theta in there. Instead of cosine 20 degrees, cosine theta. But we already know what theta is. It happens to be 20 degrees in this instance. So you leave it there. And G, cosine. And G cosine 20 degrees. Yeah, it's quite a mess, but that's it. They told you. They told you from hour one that the mass is 30 kilograms. The V, we just derived it for the B scenario, which is different from the A scenario. For the B scenario, further away, going faster, bigger radius too, 1.47 meters per second. 1.47 meters per second squared times 30 divided by 7.94 times the cosine of 20 degrees plus the quantity. 30 times 9.8 times the sine of 20 degrees. Take that top answer, whatever it is. Go down here, 30 times 9.8 times the cosine of 20 degrees minus 30 times 1.47 squared divided by 7.94 times the sine of 20 degrees. Yeah, it's a mess. It's a lot. There's a lot there. But you plug in the numbers, guys, and we're okay. And there's a lot of ways you can go here. Now, that works. I don't know how thrilled you are to see what I'm about to say, but it's a true story. Is there an M? Is there a small M right here? Is there a small M right there? Factor it out. Is there a small M right here and a small M right there? There's a small M present in all the terms on the bottom. Factor a small M out. There's a small M present in the top term, in the top here, in the numerator. There's a small M present in every term in the top. Take the small M, factor it out. Take the small M, factor it out. The M's cancel. Not that it matters. I already told you to put 30 in there. That don't matter. You got this. And that's B squared over R. Cosine theta. Again, it's aesthetically more pleasing to see theta. G, the F, again, you factor the M out there. Okay, I'll tell you in a second. I'm going to finish writing this in a second. G cosine 20 degrees. Yeah, that works. That one's better. Works better if you want to put the M in there. A little less math as you do it. Yeah. You can factor a small m out of the numerator, out of everything. Small m occurs in every place in the numerator. Small m occurs in every place in the denominator. Where all the terms have a small m everywhere. Numerator and denominator alike. Therefore, factor a small m out of the numerator and factor a small m out of the denominator. The m's cancel. The m's not even present. You got this. It worked. Anyway, you find all this stuff out, you guys. And well, we can say it that way. We write it, I think you got it in the notes as well. Let me said this. Answer the question here for B. Doesn't write quite as well over here, but is it okay? Is it okay? All right. Mu S, the end of that song and dance is 0.396. There it is. 0.396. Wow, a lot goes on here, guys. You do this for any angle, too. Conceivably, for many angles. I mean, if you put it vertical, there's no friction. The thing just falls straight out. But for everything less than 90 degrees and greater than 0, conceivably even equal to that. You probably make between 0 and 90 degrees, not between 90 degrees. This works. Let's put theta. Put a theta in here. Or put a theta in there, or you know, put a theta in there, it becomes a real abstract, aesthetically very interesting equation. There's a lot that you're doing here. You're killing a whole bunch of birds with just one stone. You're talking about friction, you're talking about resolving vectors, you're talking about knowing the period, you're talking about knowing the velocity, you're talking about centrifugal acceleration. You're talking about that fictitious force called centrifugal acceleration, which is just as big, which is mathematically just as big in terms of magnitude as the centrifugal force. Very useful stuff here when we do this. Okay? Very useful stuff. I think it really helps us out. So, there's another problem that I've done from another textbook that you probably will be looking at on your own. If you get a chance to talk about it in person one day, that'd be great too. All right, so if that's the case, let's do the last one here. And it should go pretty smoothly. The hardest one was second one. So if we're okay, I'm going to erase this, and we're going to go. We're going to do it. All right. So 75, a 0.50 kilogram ball that is tied to the end of a 1.5 meter light cord is revolved in a horizontal plane, with the cord making a 30-degree angle with the vertical. ABC, how's it go? Determine the ball speed. B, if instead the ball is revolved so that its speed is 4 meters per second, what angle does the cord make with the vertical? C, if the cord can withstand a maximum tension of 9.8 newtons, what is the highest speed which the ball can move? What is the highest speed which the ball can move? Okay, A, B, C on that one, guys. Still a little rough side, but I should go get it. I can do it. I got to run on this one. I got to make this thing happen. Basically, what they're saying is, guys, the drawing they give is this. And I'll try to run through it pretty strong. They're saying that there is a horizontal circle right here. Here's the center. Go up this way. That's 90 degrees. It's 90 degree angle. This thing right here is that. Go kind of like this. This is R. Here's the roll. This is theta. We'll talk about that a little bit. So, give me that. I'm going to do this sometimes. Here's theta. It's being revolved. Here it is. It's got that made up centrifugal force. Fc equals mv squared over r. There is mg going straight down. There is tension here. This is Ty, and this is Tx. We know that the mass is 0.5 kilograms. R is 1.5. Times the sine of 30 degrees. R is 0.75 meters, the horizontal radius. So you can say regarding this. 45 degrees. They say, how long is this thing? Let's see here, guys. Forgive me. The cord is 1.5 meters. This thing is 1.5 meters long. So this guy right here is 0.75 meters. For the radius. This is 1.5. So we did somebody did the mathematics get that. I do gotta ask you a question. This guy is firing out this way, and he's the only horizontal component. This guy is pulling back this way. This guy Tx and this guy Fc are equal and opposite. This guy's pulling in with Tx. This guy right here, with the centrifugal force, is firing outward, and Fc equals mv squared over r, and this guy's pulling in at Tx. So Tx mv squared over r. Ty is this guy. Here's Ty. And here's mg. This guy pulls up. Ty pulls up, mg pulls down. This is mg. So let's look at, okay. From here you can see a lot of this. Well, isn't the tangent opposite over adjacent? So I mean, the tangent of 30 degrees, and that's what's going on here. So you figure out a whole lot of stuff this way. So the way I did it was, I said, I'll tell you what, is the tangent of theta, which is theta is 30 degrees, equal to 30 degrees. Isn't that opposite over adjacent? Isn't that the same as TX? And if that's theta, this is also theta. This is also 30 degrees. Isn't that the same as TX divided by TY? Yeah, it's not as easy to look at. Hey, wait a minute, shoot the line on top. No, look at the triangle top. If you go here, here's the TX, here's the rise, so to speak. Here's the run, so to speak. This is TY, this is TX. TX over TY is that, is equal to mv squared over r over mg. Looks good to me. Tan theta equals, do the mathematics here, guys. What do we got here? Yeah, the m's cancel. V squared over rg. V squared over gr, you got this. You got that. What do we got? Keep going. V squared equals gr tan theta. B equals the square root of gr tan theta. Tan of 30 degrees times 0.75 times 9.8. Get an answer. Square root that answer. And that's it. And that's for that one, that part of it. It comes out to 2.06 meters per second. Sounds good to me. They're asking here if instead the balls revolve so that speed is 4 meters per second, not 2, not 2.06, but 4. What angle does the board make with the vertical? Probably bigger. So that's A. B. Let's figure it out. I mean, we say the tan of theta. I don't know what the angle is with the vertical. Now we're really going to call it tan of theta. Tan of theta, v squared over gr. Theta is going to be the inverse tangent of v squared over gr. My guess. V is 4 meters per second. 4 meters per second squared divided by the product of 9.8 and 0.75. Forgive me. Let's go back on that. Maybe we're running out of time as well. I can do this. We get to here. We got this. I'm going to say something. We'll not take it from there. Tan of theta is v squared over gr. Now, gr is not 0.75 again. It's going to be 1.5 times the sine of the new angle. That's where it gets kind of crazy. If you multiply by the sine of theta on each side, if you multiply by the sine of theta on each side, you get sine theta, tan theta, multiply by sine theta, and you end up getting v squared over g 1.5. We said this was 4. We said this before, we just square it. So this is sine theta, tan theta. 4 squared is 16. Divided by the product, g times 1.5 is 1.088. You got to really deal with that a little bit. What happens is you got tan theta is sine over cosine, so it's sine squared theta over cosine theta equals 1.088. So you got to tinker with this a little bit. We'll probably get into this a little bit next time. I'll probably just pick up here next time, and we'll just do it like that. It's a neat enough problem that I think we should do it. Just remember what there will probably merge, right? Merge the next time or something like that, or whatever we're doing. And we'll figure it out. And it should be pretty smooth. It should be pretty smooth. I mean, there's some stuff there. It takes a little bit longer, but we're good. We're good. We got the lion's share of what we want to do today. We'll pick up right here. We'll figure it out. I may have a different room for us. We may go back to the physics lab. You know, the acoustics might be a little bit better. We'll find out. We'll see what people above me think about all that. All right. Thank you. All right, guys. Good to see you again. I had to stop a little bit the last time, but we're going to merge the 2 videos anyway, so you may not really notice this, except for the fact that I'm the blockhead who just told you that we're going to be doing that. But it looks good. We've got to do it, and we're doing great. Basically, guys, the last time I was talking to you guys, I had to kind of move off a little bit. So I'm going to just start from scratch. I had to move off a little bit at 75. I was about, maybe about half done. Well, you saw the work I did up to this point right now, when I'm talking to you right now. Let me do it once again at some level. Let's talk a little bit. Let me read that over to you, and let's go. For problem number 75 from the Serway again, obviously, a 0.5 kilogram ball that is tied to the end of a 1.5 meter blackboard is revolved in a horizontal plane with the cord making a 30-degree angle with a vertical. ABC goes as follows as far as the question is concerned. A, determine the ball speed for this to happen. If instead the ball, B, if instead the ball is revolved so that its speed is 4 meters per second, what angle does the cord make with the vertical? C, if the cord can withstand a maximum tension of 9.8 newtons, what is the highest speed at which the ball can move, and obviously not breaking? So we did a good part of this problem already, as I said. You already have it. You know, just turn the film back a little bit, rewind a little bit, and there I am. Now I'm do it again a little bit. So you're looking at a situation here, guys, where you've got mg going straight down. Here it is. It's revolving around like this. This you've already seen. They told us that theta is a 30-degree angle. You guys know I try to be a little bit rigorous in matters like this. I like to keep things as symbolic as possible because it fits the whole wide range of circumstances where things can work right around a very specific angle. The very specific angle is theta, and it works for all theta in a broad range of angles of theta. However, they did tell us 30 degrees, so I'll put theta here, I'll set it with 30 degrees and go from there. There is a component, vertical, downward, called mass times g, and g going straight down. There is a component of tension. This is the tension T. There's a component of tension in the vertical direction called Ty. So Ty is equal and opposite in magnitude to mg. There is Tx going this way to make your right triangle work. By the way, this is 30 degrees. This is theta, which is 30 degrees. This is also theta, which is 30 degrees. They're alternate turn range. Then this and this. This and this are parallel lines. And that goes, that's transverse to custom. Alternate turn range. Here's Ty, here's Tx, here's T. TX, you can kind of view it as happening here as well. Don't double the two. Don't go TX plus TX. One TX. Just put the TX right here. TX and FC, centrifugal force. Well, they got to be equal. So the TX is the centrifugal force pulling it in. If you want to kind of throw out the fictitious force that way and have them cancel out, which I like to do, the centrifugal force, then you're okay. TX is equal to mv squared over r. Again, guys, if this looks familiar, we saw this earlier in the tape. You actually did see it earlier in the tape. I'm going to keep going. I didn't need to do it. It's really good. So we got this. We're all seeing this again. So we're looking at this. Stuff just takes so long. There's no way I'm going to fit that. We probably need another half hour to get it done last time. So we got to just go at our pace. We feel we got to do here to stay under control. All right, well, tell you what can you know? What do you know? Okay, first of all, they said a bunch of stuff here. I mean, that I kind of ignore. They're telling us the cord, the length of the cord that's holding this thing, and this thing's spinning around. It's not just being held here, it's being spun around. And we can see these dashed lines I put up there. You know, they're looking pretty good. Okay. So you see the dashed lines going up here, so it's kind of spinning around. If this is 1.5, then 1.5 times the sine of theta will give me this length right here. And that's the radius. And this is pretty much the pseudo radius. It's the radius of the circle. So the radius of the circle is 1.5 times the sine of 30 degrees. That's what we're getting back from. Okay? Gotta talk some more. If this is theta, and this is ty, and this is tx, if you go tx divided by ty, that's the tangent of theta. Don't always think y on top, x on the bottom. Yeah, I get it. You're right. It's true. Look at the substance of what's going on. I told you guys that great professor I had a long time ago, he said they won't hire you as an engineer for something that you can just look up. They'll do that themselves. They won't hire you. You got to look beyond that. And that's what we're doing here. If this is ty and this is tx, you can kind of say that's the line that way. And this is the run that way. And this is tx over ty. Which is equal to what? So there's a lot of ways to do this, but let's is that true? I think so. Tx is mv squared over r. Ty is mg. There it is. The m's are going to cancel. And you got, at the end of the day, you got this. Okay? They're asking 3 questions, but this stuff is easier done than said. Let's just talk. I mean, they're sitting here, there it is, set up like that. There's a 45 kilogram ball inside the one end of a 1.5 meter whiteboard. It's revolved in a horizontal plane with the core being a 30-degree angle vertical. A, determine the ball speed. Pretty easy. B, if instead the ball's revolved so that its speed is 0.4 meters per second, what angle is the core making the vertical? Not too bad. C, if the core puts a maximum tension of 9.8 newtons, what is the highest speed which the ball can move? Again, I'm going to go on the stuff I said last time, guys, so we'll go a little bit faster, because you already have You multiply by j inside, you solve for b squared. You square root inside. V equals gr tan theta. Sounds good to me. What does that mean? G is 9.8. R is 1.5. The tangent of 30 degrees is whatever it is. Theta is 30 degrees. 9.8 times 1.5 times the tangent of 30 degrees. Get an answer. Square root of the answer. You get theta. It's that simple. It's that simple. Well, I know the answer. We write it out and see what we got. Well, as we got last time, we got this time. And again, I just want to start from scratch. I think you're going to get more out of it. There's an old, I studied Rotational a long time ago. Not that good at it, but I practiced a little more. An old, one of my old professors, she had said, and other people had said too, repetition is the mother of learning. It's good to see study. Nothing wrong with seeing something again. Nothing wrong with it. Get a different look at it. You can get a different view of it. Even if you don't think, what's the point? Believe me, sometimes even seeing it again, you get a new perspective on it. A new perception of it, so to speak. That's been my experience. I can tell you that. That's 75A. 75B. They're asking an interesting question here. That's tough. And I think this is where we left off. So let's take our time, because we got a lot of time now. Let's take our time. B, if instead the ball is revolved so that speed is 4 meters per second, what angle is forming the vertical? I don't know, I guess it didn't make an angle that's bigger. I guess it's going to be a bigger angle than 30 degrees. That's my knowledge. I got to test it. I got to find out. I got to work on this. We got to do mathematics and physics. We got to do the constructive intuitive thinking. All that's required to be able to solve problems. I mean, I'm looking at it and I'm thinking, okay, well, you saw the whole song and dance we did. It's fine. Here's where the theta, you can blow off this thing at a 30-degree angle. It's no longer 30 degrees. If this thing's going to move around, this is going to move around a certain way. Now, the theta is not necessarily going to be a 30-degree angle. Very likely not going to be. For certain, not going to be a 30-degree angle. For certain, what's going on here? Try to think. Perhaps, the way I did the problem, the way I did the problem, I'm going to stay here. I'm going to sort of stay here, I should say. I'm going to stay here or here to look at this. You'll see what I mean in a second. Coming to B, what is the angle that's going to, what angle is going to be in existence in this configuration, this problem? What angle do we have with the vertical if the rotational speed in that horizontal plane is now 4 meters per second as opposed to being only a little more than 2 meters per second? Well, if it's going roughly twice as fast, my gut is telling me it ain't going to be good. But at the end of the day, you can't just go here. You can't just go here. The reason you can't just go here, or can't just go here is, I gave you this. I gave you this. I don't know that. And I don't know that. Because R, let's break this guy down. We don't know what the new radius is. When this thing opens up, when this thing opens up, R is bigger, theta is bigger, you got two variables. You really got to watch what you're doing. You really have to watch what you're doing. Feed this guy in your memory. Feed that guy in your memory. Let's talk. R G, R. R is 1.5 times the sine of theta. It's not the sine of 30 degrees. We just discussed the fact we don't know what theta is. We're trying to find it. So there's a lot more variability here than maybe initially meets the eye. The tan of theta is sine theta divided by cosine theta. You look at the trigonometry. So we got that. Why don't you multiply by the, let's see here. Why don't you multiply by the sine of theta on one side? Multiply by the sine of theta on both sides again. Yeah, looks okay to me. Let me see exactly how far we get this. It should be pretty straightforward. Let's talk. Didn't they hypothetically propose the speed of 4 meters per second? V is 4 meters per second. V is 4 meters per second. 4 meters per second squared is 16. This is 9.8. This is 1.5. 4 squared, 16. 16 divided by the product of 9.8 and 1.5. When you find that out, plug in the appropriate values, we still, look, this is still a mystery. I mean, there's a lot here. Knock this around a little bit, guys. We're down to here. Not done, obviously not, but we got this. So let's see. This is a great problem. Can we get out of this? There's a lot here. There's kind of a clever way to get out of this. Be careful about it. You guys remember, first of all, you remember a bunch of things. You remember that the tan of theta is sine theta over cosine theta. You remember that sine squared theta plus cosine squared theta. Yeah, we know that. We've got the background on this stuff. Trigonometric identities you can look up on various books, including our own book. We got this. Tell you what, I've already taken advantage of this to do something. Now we'll take advantage of that. Why don't I subtract cosine squared theta on each side? I have sine squared theta equals 1 minus cosine squared theta. Sine squared theta equals 1 minus cosine squared theta. So this guy right here is 1 minus cosine squared theta. Over cosine theta. Somebody might look at that and think, all right, Dale, what are you doing? You're doing a bunch of mumbo jumbo here. Well, maybe it's a little more manageable because I don't have different trigonometric labels or identities or different trigonometric quantities being mentioned. I've got essentially one trigonometric quantity being mentioned, and that is all of this is in terms of some manifestation of the cosine theta. This expression has the cosine theta associated with it. So there we are. We got this. I'll tell you what we'll do. We see to multiply by cosine theta on each side, and then get everything on one side instead of making it 0, and then do the quadratic formula. At the end of all this, let's do it. Let's see what we can say about it. I'll go up like this. So I should have some kind of online goal with you guys. It's going to be easy to live this time or light to live this time. It's always a different story, but we'll see what happens. Not bad. There it is. Play the game. Why don't you take that, the bottom right hand side, up there on the board, multiply by cosine theta on each side, and then get everything over to one side instead of equal to 0. Look, I'm going to make a long story short. You heard what I said. I think that's the issue. It is an interesting problem. Minus 1 is the same as plus or negative 1. Guys, what am I doing? Well, you see, put a 1 right here. 0 equals ax squared plus bx plus c. X equals the opposite of b plus or minus the square root of the quantity b squared minus 4ac. The whole thing over 2a. The whole thing over 2a. What's going on here, guys? Look at it. Cosine squared, x squared. Cosine, x. Negative 1, c. 1 is the a. 1.088 is the b. Negative 1 is the c. A equals 1, b equals 1.088. C equals negative 1. X equals cosine theta. X squared equals cosine squared theta. Obviously, well, that's cosine theta. Anyway, that's the game you're playing. X is the cosine theta. You're solving for cosine theta, and there you're going to tinker with it. What are you doing? That guy right there, essentially, you got the opposite of b plus or minus the square root of. The opposite of b plus or minus the square root of this entire map. Guys, this right here is the same thing. I played the game, like I said. What's going on? We end up getting, we end up getting a couple things here that we're not going to worry. We end up getting x equal to the cosine. You set x equal cosine theta, and that's 0.55945. We also get x is equal to cosine of theta is negative 1.682. There's something wrong with that. The cosine function has its maximum at 1. The absolute value The minimum absolute value of the cosine function is 0. The cosine function in terms of absolute 0 is between 0 and 1, potentially inclusive of either one. This is absurd. Mathematically, I arrive at it, but it has no basis in the reality of the question that's being asked. Just not possible. I got a question for you. Theta is the inverse cosine. Now let me just give myself some room here. As I mentioned, I'm the only person probably in the city that has a 50-meter board and doesn't have enough room, I guess. So let me go down here and say theta is the inverse cosine of this. Simple math. That's 53.53. 53.52 there. Let me just put it right here, guys. I ran out of room here. Theta is 53.52. 53.52 degrees. We said it was going to have to be more than a 30-degree angle. If you're whirling that thing around, it kind of gets picked up in a sense. So there it is. That was important. That was important for us to do that. A lot there. What's great about these problems, you guys, so that's A and B so far. We just did A and B. What's great about these problems, you guys, is there's so much in these. Some problems more than others. In very many of these problems, there's so much there. You're killing a whole bunch of birds with one stone. All right, the other one should go a little more straightforward. So let me see what we can get. Let's go over to C. Okay. So you guys are all right with this? We have what we have. We need A and B. Let's clear things out a little bit. And then hit C. All right, so we set up a bunch of stuff here. Let me erase this. Let's go with C. The argument is pretty straightforward. Okay, let's see. This last problem that we did, 75B, is pretty fascinating in that you really have to think around a number of things. You have to know the algebra, you have to know the trigonometry, and you've got to know a lot. There's a good amount that you have to know, which makes it a great problem. It simply makes it a great problem. Okay, so here they're saying that things will break at a tension of 9.8 newtons. What is the highest speed at which the ball can move? They're still doing it to us. They're still kind of playing that game. Let's argue. Let's do a few arguments here. Figure out what we're doing. 75C. Here's your maximum potential allowed, you guys. based on the mathematics that we had done earlier, based on the analysis that we had done earlier, is this. Okay, just forgive me 1 second here, guys. There's something looking at right now. I should rewrote that a little bit. TY is this, we know that. We've been now again, it's a little counterintuitive based on some of the arguments that we've given in the past. I get that. The argument that matters is what you have visualized and then making everything correspond to what is visualized. What you drew discusses the matter. Adjacent to the hypotenuse is loci. Doesn't matter if it's TY. I know, hey, y is a huge sign. X is a huge cosine. No. The triangle looks what it looks like. Look at the triangle and forget the labels. Look at the triangle and then evaluate what the cosine would be looking at the triangle. Based on looking at the triangle. What would the sign be? Looking at the sign. So this is okay. Basically what we're saying here is the T cosine theta, Ty, is this, is equal to mg. So that's how I have. T is equal to mg over the cosine theta. Solve for t, you get to here. You can keep playing it here. Go back up here and solve the cosine if you want. We got this. Yeah, I mean, it looks about right. I'm just trying to, for some reason, I'm looking at some of the arguments I made later on, and I'm trying to say, I just don't want this to get too deceptive. It comes across as separate easy, but I think there's more to it. Yeah, it is the idea of the way they're asking here is, what's the highest speed? I can get the angle, now how do I get the speed? Well, first things first. Got this. The theta for this maximum tension to occur. And again, you guys, I don't want to sound like a broken record here. All of this and more is on camera. We'll get there. Theta is this. Theta is the inverse cosine of this right here. Fine by me. What do you got? Theta is the inverse cosine of 0.5 times 9.8 divided by maximum tension, this. 9.8 divided by 9.8 is 1. The inverse cosine of 0.5 theta is a 60-degree angle. That's pretty important. I don't lie other ways. Because we found out if you went to 4 meters per second, you had, if we were back, let's see where it was. We had a 53 and a half, roughly a 53 and a half degree angle. Roughly a 53 and a half degree angle. This is even more than that. Which means what? Which means it's going faster, it's probably going faster than 4 meters. You know that? So we got this. If that's the case, you gotta remember what we were talking about last time. Didn't we say that the tangent of theta was equal to Tx over Ty, which is mv squared over r over mg. You got this? Yeah, you do. Multiply by gr inside, square rooted. Yeah, I mean, we've been there. We've definitely been there. And in fact, we're just about to be done. G is, well, yeah, you guys spoke too soon. Oh, maybe I didn't actually. Let's remember what's going on here. What's R? R is equal to 1.5 times the sine of theta, the sine of 60 degrees. So I'm going to put that in there. G is 9.8. G is, as we said, G is 9.8, R is 1.5 sine 60 degrees. The tangent of theta is the tangent of 60 degrees. Okay. That's about 1.3. That right there is about 1.3. This is 9.8. So we got 9.8 times 1.3 times the tangent of 60 degrees. Get an answer. 9.8 times 1.3 times the tangent of 60 degrees. Get an answer. Square rooted. Find out what we need. Our gut tells us it's going to be more than the 4 meters per second that we had earlier for the 50, for about, what was that, roughly the 53.5 degree angle. This is a 60 degree angle. I think it's going to be more than that 4. That's the maximum. If they go any faster than that, you're going to break it. The tension ain't going to hold. This is the maximum speed you can get it to go at. The numbers they gave you are what they gave you. For this to be, try to think here. There's a lot that goes into this. I mean, more than, there's a lot that goes into this. You're not going with the tension that you're allowed to have, or the tension you're allowed to have, the maximum speed is 4.7 meters per second. All right, as you can see, even doing one part of one problem can itself be a lecture itself, right? Or even one problem can have turn into a lecture by itself, and it takes a good amount of time. But anyway, so that is it. I thank you for this part, and that's going to get, and we're good. We're chapter 7, we are done. Thank you.